absorb what
you're ending your day now.
Yeah, that's it. Oh, the webinar is live. So Swati, I'm just going to switch off my camera and mic. Okay, so you're the boss now. Right.
Okay. I think I'll wait for 3 minutes more, and then we'll start.
Yes. So I think some more people will be joining in 2-3 minutes, and then we can begin at sharp 6:30.
Yeah. Okay.
But we don't have any parallel sessions now in a way. Right?
No. Only
only the morning ones. There's that time constraint is really binding.
Right. So Professor Woodford, so I had a small question. So, I mean, have you seen or yourself, I don't precisely work on this area. I work on mechanism design and game theory. So, but at one point of time at my earlier workplace, I had to teach some growth. So I had to look at some micro foundations of, this dynamic models and so on. So I was wondering, we worked with this models of representative households and so on. And these were fairly straightforward Arrow-Debreu sort of models with time incorporated. So, are people coming up with this kind of limited cognition models, giving micro foundations with respect, to representative household models and so on?
Well, there are models that that incorporate cognitive limitations into models of dynamic decision making of the kind that are used in growth models or models of the effects of monetary and fiscal policy. And I've been doing some work of that kind. I'm going to be talking about simpler issues in modeling economic decision making in these lectures, but I have some recent papers that talk about how the effects of monetary or fiscal policies change when you incorporate cognitive limitations into models that would otherwise have the structure of a dynamic general equilibrium model.
I see.
And the answer is, well, some of the results from the standard literature do carry through as at least limiting cases of the parameterization of these models, but some conclusions are quite fragile. And so the thing I've mostly been interested in is understanding which of the results from the rational expectations analyses are approximately correct if people behave sensibly but not perfectly, and which of them fall apart quite easily if they're even small departures from perfect rational expectations.
But as a follow-up to Shaumendu's question, Michael, so how does one aggregate this kind of thing? A representative agent model, it's, you don't have to aggregate at all. But here you are getting different kind of signals, so to speak, from different kind of people. So do I look at the average, and then how does that capture this,
Well, at least for many decisions, the answer is yes. You can look at the average of the decisions of different people. So if you're interested in modeling aggregate consumption, you add up the consumption decisions of the different households, and that average is your prediction about the dynamics of aggregate spending. In the case of models of price adjustment, and a general price index for the economy is something you're interested in the dynamics of, and that might be a nonlinear average, but it's essentially an average of the price setting decisions of the different firms. And so these models do introduce individual level heterogeneity coming from the idiosyncratic randomness in these mental representations, even if not from other things. But you still are, in macroeconomic modeling, you're generally interested in the evolution of averages of these behaviors of the different people.
Okay, good evening, everyone. A very warm welcome to Professor Woodford and all of the participants to the second session of the lecture series. So Professor Woodford is Professor of Political Economy at Columbia University, and his current research work lies at the intersection of behavioral economics and macroeconomics. So we had an illuminating session in the morning where Professor Woodford had talked about randomness of choice and how imprecision of comparisons and choice can be modeled. So he'll be delving deeper into this topic, and in the second lecture of the series, he'll be talking further about the anomalies associated with choice under risk. So before we start, a couple of quick reminders. So if anybody has any clarificatory questions, please put it in the chat box. And in case if you have some other questions, I'll try to take them up after the talk. If time doesn't permit, then in that case, we have a breakout session at 10:15 p.m. IST today, and participants can have a one-to-one interaction with Professor Woodford during then. So please do register for that. Thank you. Over to you, Professor Woodford.
Okay, thank you. Welcome back, everyone. And just to remind you what we've, my screen is not moving. Okay, what we've been talking about. In the earlier lecture today, we've argued that it's useful to model decisions as being based on imprecise internal representations of the data that define the choice problem, rather than assuming that people's decisions are a function of what the objective features are of the things they can choose. So the objective rewards, for example, associated with the different choice options that they're presented with. And in the models I was talking about, this imprecise internal representation is not only simplified, but in particular involves random noise. That hypothesis then implies that decisions have a random element, but it doesn't just imply that decisions have this random element. It also implies that people's decisions should be based on subjective evaluations of the options that they face, and those subjective evaluations will typically involve systematic bias. They won't just vary randomly around the correct valuation, but often be different on average from the correct valuation. Even if we suppose that someone's decision rule is optimal, meaning that their rule for deciding does maximize their average reward across decision problems, if they maximize average reward subject to the decision rule having to be based on this noisy representation, in general, that will result in decisions that are being based on these systematic biases. We illustrated this idea of there being systematic biases as a result of noisy internal representations earlier in first lecture, in particular by talking about a Bayesian explanation for the so-called central tendency of judgment. And that was a systematic pattern that's observed in perceptual judgments in many different perceptual domains, where smaller magnitudes tend to be systematically overestimated and larger magnitudes systematically underestimated. And we talked about evidence of that and the Bayesian interpretation of it. Now, the fact that I want to talk about more in this lecture is that the fact that biased estimates are actually optimal when those estimates of, say, a sensory magnitude have to be based on a noisy internal representation is something that I think can provide a functional explanation for some of the behavioral biases that are observed in economic decisions. So patterns of behavior that are not consistent with rational choice, at least with fully informed rational choice, where people are responding to a correct understanding of the things that they're choosing between. Such patterns that are often considered mysterious might actually be patterns that are serving people well on average if we take it as a constraint that their minds have in some way to economize on the degree of precision with which they're taking account of the particular situation that they're in. So that's an idea that I want to pursue. So as I think I've already illustrated some in the first lecture, limited information of this kind does seem to be clearly an important issue for understanding the accuracy of people's sensory judgments. These are demonstrably not just inaccurate, but systematically biased in particular ways that can be explained by this hypothesis that the judgments have to be based on a noisy internal representation. The question we want to pursue further is this source of bias also important for economic decisions as well? And so what I want to talk about in this lecture are some puzzling features of people's attitudes toward choices under risk. And so I want to talk about what are sometimes broadly called risk attitudes, which are departures from risk neutrality in decision making. The observation that people don't behave in a perfectly risk neutral way is a very old one. It goes back to early discussions back in the 18th century by the developers of probability theory. One of the first applications of probability theory that people had in mind was using it to analyze gambling behavior. And an early proposal was, well, perhaps the rational thing to do is to accept gambles if they're mathematically fair gambles are better, turn them down if they are less than a mathematically fair gamble. So that would mean that the mathematical expectation of the payoff being larger or smaller than the amount that you have to bet would determine whether the gamble should be taken or not. It was immediately observed that actual gambling decisions didn't seem to conform to that principle. And of course, there's a very familiar standard explanation that we teach in economics classes. And this standard model postulates that people don't, in fact, in general, seek to maximize their expected financial wealth, the mathematical expectation of the wealth that they end up with, but instead to maximize the expected utility of wealth. And under the hypothesis that the utility of wealth is some increasing function of wealth, but not a linear function, then these two hypotheses are not the same. So Daniel Bernoulli, in particular, introduced this idea pretty early in the 18th century as an explanation of risk aversion in people's choice with respect to gambles. He pointed out that if this utility of wealth function was increasing but strictly concave, then the concavity of the utility of wealth would imply risk aversion. He suggested maybe the logarithm as an example of a reasonable type of utility of wealth function. But while this idea can explain risk-averse choices, in principle, the idea that people maximize the expected utility of wealth, where utility of wealth is a nonlinear function, could also be consistent with risk-seeking in some cases. And there's a famous paper by Milton Friedman and Jimmy Savage from back in 1948 that illustrated this as a potential explanation of gambling behavior. They proposed that people's utility of wealth functions often had a region over which it was convex, even if it wasn't globally convex, and a decision maker whose current level of wealth was at the level where their utility of wealth function was locally convex could then choose to take gambles consistent with maximizing their expected utility of wealth, even if the gambles were not mathematically fair bets. Okay, so those is a familiar line of explanation of departures from risk-neutral decision-making, but I think there are important problems with this theory that explains risk attitudes as a consequences of nonlinearity of the utility of wealth function. So one simple problem that we've already referred some to in the earlier lecture is this is a theory that implies that a decision maker should have a definite preference ordering between any two simple gambles. Any two gambles offer two different probability distributions for your eventual wealth level. You can evaluate the expected utility of wealth for each of them, and you should have a definite preference between the two, except in extremely special cases where they might be exactly equal and you would be perfectly indifferent. Instead, what one observes is that choices between simple gambles have an apparently random element, as I already talked about in the earlier lecture. And so this is, again, this figure from the paper of Mosteller and Nogi back in 1951 that I already showed you in the first lecture. In this figure, Mosteller and Nogi are conducting a laboratory experiment intended to test the von Neumann and Morgenstern theory of expected utility maximization as an explanation of decision under risk. They want to collect data and see if the data of their experimental subjects can be fit by some von Neumann-Morgenstern utility function. They want to find out what the function would have to be like. The figure is illustrating how the experimenters locate one example of a calculated indifference point. So they're varying the amount that this gamble can pay off on the horizontal axis. They want to know how much the gamble has to pay off in order for the subject to be indifferent between taking the gamble and having 5 cents for sure. And the figure was showing how they calculate the indifference point. What I want to point out about the figure is not the location of the indifference point, or at least I'll come back to that. But right now, the thing I want to point out about the figure is not that you can calculate this indifference point, and it might make sense, but that one sees random behavior here. And the figure is really not consistent with the von Neumann-Morgenstern theory that the authors were trying to fit to their experimental data. The von Neumann-Morgenstern theory says there should be an indifference point. It can explain why the indifference point might be at the location that it is, but it implies that for values of the payoff less than this indifference point, the subject should never take the gamble. And for values more than that point, the subject should always take the gamble. And instead, what we're seeing is a gradually increasing probability of taking the gamble. But both to the left of the indifference point and to the right of the indifference point, we see randomness of the subject's behavior. Okay, so that's a puzzle, but maybe not a big puzzle. I already talked in the earlier lecture about extending rational choice theory to allow for random choice in the way that, for example, random utility models do. So introducing randomness in the comparison process between different options. You might think, well, that's enough to explain this figure. So I'm going to go on to some other puzzles for the nonlinear utility theory of risk attitudes. And another puzzle is that if we explain risk aversion as being due to diminishing marginal utility of wealth, as Bernoulli proposed, then that theory allows for risk aversion as a consequence of concavity of the utility of wealth function, but it implies that the degree of risk aversion should become negligible if you make the stakes of the gamble small enough. What one instead observes is aversion to bets that are even somewhat better, non-trivially better than mathematically fair bets, even when the stakes are made quite small. And as Matt Rabin pointed out in his 2000 paper in Econometrica, this is in fact a puzzle because it's hard for the same utility of wealth function to be reconciled with risk aversion in the case of very small bets without it also implying extreme risk aversion in the case of larger bets, and we don't also see that. So about this presence of non-trivial risk aversion, even for very small bets, I want to show you again the Mosteller and Noji figure, and now look at where the indifference point is. So this is a case where you get the amount X on the horizontal axis with a probability of 1/2. You get 0 with a probability of 1/2. So a risk-neutral decision maker should value the gamble at X over 2. Since you have to pay 5 cents to take the bet, the indifference point should be exactly 10 cents. Instead, the indifference point is more than 10 cents. It's about 10.7 cents. Now you might say, okay, well, that's only a little bit of risk aversion. Mathematically fair bet would be if it paid off 10 cents. Instead, the subject requires it to pay off 10.7 cents to be indifferent. That's only a little more, or it might seem like only a little more. If you ask how curved does the utility of wealth function have to be for the marginal utility of wealth to be declining enough when you increase your wealth by 10 or 11 cents, in order to reconcile having the indifference point at this point, you conclude that marginal utility of wealth is declining so rapidly that this subject would have to be indifferent between a bet that offered them an unbounded amount of money, whatever number of trillions or more of dollars you might want, if the bet pays off, if they had to put up 55 cents as the amount that they had to gamble instead of only 5 cents. Okay, and of course that's absurd, that people would not be willing to gamble an amount less than $1 to have a 50% chance of earning all the wealth in the world. And so the same degree of curvature of this utility of wealth function cannot in fact reconcile those two aspects of people's behavior. Now, there's a common response to this in the literature on experimental economics. And the common response, and one that, for example, Rabin discusses himself in his own work on this, is to propose that subjects don't, in fact, maximize the expected utility of their total wealth, where total wealth means we integrate the amount they earn from the experiment with the rest of their wealth to define an overall lifetime budget constraint, and it's the utility that they can achieve from that overall lifetime budget constraint that they want to maximize. Instead, the hypothesis, common hypothesis, is that people seem to have some nonlinear utility function from their earnings from this individual decision, say from this laboratory experiment, taken in isolation from the wealth that they have from other sources and that they use for other things. And if you have this hypothesis of a separate nonlinear utility for the earnings from the experiment, then you could have significant curvature, even at small variations in those earnings, without it necessarily implying that the marginal utility of wealth is also sharply decreasing for larger changes in other aspects of your overall wealth. Now, a question, though, about whether you should be happy with that as an explanation is, well, is that really consistent with a model of rational decision-making, where people understand exactly what their options are, what the consequences for their total lifetime plans are of doing one thing or another in the experiment? If you say these are people's true preferences, they represent well-considered preferences, I think that poses the question, well, why are the preferences of the individual that they care about these individual little increments to their wealth separately, rather than only caring about the indirect utility of their overall lifetime budget? If you say they correctly understand the consequences for their life of getting more money from the experiment or getting less money from doing the experiment, why exactly does it make sense for them to care about those outcomes in that particular way? I'm going to propose a different line of explanation in this lecture, and it's a proposal that people's failure to perfectly integrate the earnings from some individual choice problem with the rest of their wealth is in fact going to be a natural consequence of supposing that their decision has to be based on an imprecise internal representation of the situation that they're in, rather than on a precisely accurate understanding of that situation. And I'm going to suppose that their decision rule is optimal, optimal subject to the constraint that it's based on this imprecise representation of the situation, optimal meaning optimal for their overall expected level of utility from their overall lifetime budget. So I'm going to assume that my optimality criterion is one under which only your overall lifetime budget matters. It doesn't separately matter how much you earn from one source or from a different source. Nonetheless, this kind of behavior where people look as if they have a nonlinear utility of wealth for the earnings from the individual decision in the experiment is going to come out as a consequence of the theory. A third kind of puzzle that I want to mention is that one observes in the laboratory that the same subjects can be both risk averse and risk seeking, depending on which decision problem you present them with. And this is something that Kahneman and Tversky talk a lot about in their famous 1979 paper where they introduced prospect theory. I've pointed out that the theory of expected utility maximization is in principle consistent with either risk-averse decisions or risk-seeking decisions. If you assume the utility of wealth function is locally strictly concave, you predict risk aversion. If it's locally strictly convex, you can get risk seeking. But what the model implies is that in the case of any bets that are being considered, if the bets are small enough so that it's only the behavior of the function relatively close to your current wealth level that matters, then either a given person's utility of wealth function near their current level of wealth, it's either locally concave or it's locally convex, but it can't be both. There's no function that would be both. And so either for all small enough bets, they should be at least moderately risk averse, or for all small enough bets, they should be moderately risk seeking, but you shouldn't be able to observe significant risk aversion and significant risk seeking by presenting them with different types of relatively small bets. There would be no single utility of wealth function that could do it. Instead, Kahneman and Tversky point out that they can observe both kinds of behavior, either in the same subject answering different questions at different points in the experiment, or with subjects randomly selected to be presented with one question or a different question, but systematically behaving in different ways, even though it was purely random which question they were selected to answer. So I want to illustrate this combination of both risk-averse choices and risk-seeking choices that Kahneman and Tversky talk about. This is one of the pairs of decision problems they consider in their 1979 paper. So one question is, they present to their subjects, in addition to whatever you own before you make this decision, you're given 1,000. And let's suppose these are, say, $1,000. It's some non-trivial, but not life-changing amount of money for their experimental subjects, and it's a hypothetical decision. Suppose you're given this additional $1,000. You're now asked to choose between two options, A and B. If you pick A, you'll get an additional $500 with certainty. If you pick option B, instead the outcome is random. You're taking a gamble that has a 50% chance of winning you another $1,000, but it has a 50% chance of winning nothing. So you'll only have the original $1,000. A second version of the problem has a similar structure, but the numbers are different. In this problem, the subjects are asked, in addition to whatever you own, suppose you're given $2,000. You now have to choose between two options, A and B. If you pick A, you're going to lose $500 with certainty. If you pick option B, the outcome is random. There's a 50% chance that you'll lose $1,000, 50% chance that you lose nothing. Okay, so you may have your thoughts about what you would prefer between A and B. In the case of Kahneman and Tversky's subjects, a large majority of the subjects pick A in the case of that first problem, and a definite majority of the subjects pick B instead in the case of the second problem. So what's puzzling about that, though? The puzzle here, as some of you will probably have noticed, is that the majority of people are risk averse. In one case, the majority of people are risk seeking in the other case. So in problem A, the majority go for the risk averse, are apparently risk averse, because in the case of two gambles that give you the same mathematical expectation, they prefer certainty to the random outcome. But in problem B, the majority prefer the random outcome to certainty, although again, the mathematical expectation of the two outcomes are the same. So risk aversion in the first problem, but risk seeking in the second problem. There's an even bigger puzzle that some of you will have noticed, which is that in both cases, these subjects are in fact choosing between the same probability distribution over final wealth levels. In both problems, if you take option A, you end up getting $1,500 more than you started with certainty. And in both problems, if you pick option B, you have a random outcome, a 50% chance of ending up with $1,000 more than your initial wealth, and a 50% chance of ending up with $2,000 more than your initial wealth. So the only difference in the two problems is, in one case, you were given 1,000, and then you can get a random increment to that $1,000. In the second case, you were given 2,000, and you can lose a random increment, a random decrement from that gift of $2,000. Okay, so this is a puzzle because no utility over final wealth is going to have the property that maximizing the expected utility of final wealth could lead to one decision in one problem and a different decision in the other problem, given that the choices between probability distributions of final wealth levels are actually the same in the two problems. Okay, so what do Kahneman and Tversky think is going on here? Their explanation is of the kind that I mentioned earlier. They suppose that people don't integrate this initial gain, the part of the problem that says, suppose you're given $1,000, then you make a further decision. They suppose that people don't integrate that initial gain with the subsequent gains and losses that they get by picking A or picking B. And so they don't analyze these choices in terms of their consequences for final wealth. They call this an isolation effect. An isolation effect meaning the subject considers the consequences of picking A or B in isolation from the fact that they got a certain amount of money earlier before they picked A and B. Okay, so in that case, the two problems are no longer equivalent if you only consider the consequences of an A and B, because those are different in the two cases. That's, of course, not enough to explain why people should behave on average differently in those two cases, because we, again, are considering two problems where the mathematical expectation of the payoff is the same for A and B in both problems. And to explain why people would go for certainty in one case and go for the random outcome in the other case, you have to be able to postulate risk aversion in the case of the choice between the random gain and the certain gain, but risk seeking in the case of the choice between a random loss and a certain loss. And that's what Kahneman and Tversky proposed. They proposed that, in fact, people evaluate random gains versus certain gains with a value function which is concave in the case of gains, but they evaluate random losses versus a certain loss using a value function which is strictly convex in the case of losses. And so this value function has a concavity versus convexity that depends on the sign of the net gain, whether it's a positive net gain or a negative net gain. Okay, so they can make assumptions which they propose as part of prospect theory that can explain what's going on in both of those problems. It does seem to be an explanation that requires you to introduce several logically distinct hypotheses that all have to be true. In recent work with Mel Kaw and Zhang Li, we have a paper that proposes that all of these things that I've been talking about, the randomness of choice between these simple gambles, the so-called isolation effect, risk aversion in the case of small gains, risk seeking in the case of small losses, can all follow from a single underlying explanation. And it's this idea that decisions are being based on an imprecise, noisy mental representation of the data describing the decision problem, where the nature of this noise in the mental representations that you need to explain these things is the same in all of those cases. What kind of noise should we assume? So the conclusions we're going to reach about biases are going to depend on, if we want to interpret those biases as representing optimal decision rules, given the noisy internal representation, the nature of the bias that's predicted is going to depend on what we assume about the noisy internal representations. In particular, it's going to depend on whether the degree of imprecision in these internal representations is uniform or variable over the range of possible true values. And that was an idea that also came up earlier this morning in the first lecture. I talked about another experiment where the bias in people's ratings of food items that they could get from the experiment was in fact different for different items. And the way the bias changed with time pressure was different. And we were interpreting this as non-uniformity of the degree of noise in the internal representations in the case of the different food items. So that turns out to be a crucial issue. And you may be wondering, so what should I assume about that for a model of the kind of decision making that's involved in deciding between these simple gambles? What, in fact, would it be reasonable to assume about the noise in internal representations of the available monetary payoffs in simple gambles of the kind that we've just been talking about? One way of getting an answer to this, rather than just allowing complete flexibility and asking, well, what can I assume about the noise that can reconcile the observed behavior in those experiments? One way of disciplining our way of thinking about this is to look at another source of evidence, which is evidence on the imprecision in people's perception and internal mental representations of numerical magnitudes in other contexts. They're not about monetary payoffs in gambles, but just trying to understand more about imprecision in the way people's minds represent information about numbers. There's a lot of evidence, as I mentioned already in the first lecture, that at least when people make quick judgments about numerical quantities, and this includes judgments about the sums of numbers or averages of numbers, if they have to do this maybe quickly or under circumstances where they're not treating it as an arithmetic problem and trying to remember do mental addition or mental division, remembering facts of arithmetic that they were taught in school, but simply using their sense of how big these quantities are, then it seems that people can make quick judgments about these things, but that the judgments they make are based on imprecise mental representations of how big or small a given number is. And the errors in these judgments can be explained by assuming that people are using what the psychology literature calls an approximate number system that postulates that there's an internal mental representation of the meaning of these numbers that's fuzzy in the same way that the mental representations of sensory magnitudes like lengths and areas, brightness, speed of motion, and so on are similarly imprecise. In particular, Stanislaus Dehaene, who has a whole book on this called The Number Sense, argues that the imprecision in these internal representation of the meaning of numbers is similar in its structure to internal representations of physical magnitudes like length. And in fact, he argues that these imprecise mental representations of numerical quantity are in a similar brain region close to the one involved in representing physical magnitudes like length. In particular, this brain region that's involved in representing the meaning of numerical information, even when the numerical information is presented with number symbols, seems to be the same one that's involved in representing number information presented in a different way, which is representing the numerosity of visual arrays. So there's an array with many items in the same picture, and people can form a quick sense of how many or how few those items are. That's what we mean by numerosity. The way this feature of a visual array is represented in the brain seems to be closely related to the way that the meaning of number symbols are represented. And so we can learn something about the nature of the imprecision in the brain's representation of number information for studies of errors in people's judgments about numerosity. And this issue of judgments about numerosity and how accurate or inaccurate, how biased or not they are, is something that's been studied extensively in experimental psychology, and so that's why I wanted to talk about it. In fact, careful quantitative studies of this have gone on for a long time, more than 150 years. It might interest some of you that one of the first people to publish an experimental study on this issue of how accurate judgments of numerosity are was William Stanley Jevons, a name that some of you will know as one of the founders of the development of neoclassical economics, the originator of concepts like marginal utility. He also studied experimentally this issue of the accuracy of judgments of numerosity and published a paper in Nature on this in 1871, one of the first experimental studies in this area. So it's not completely eccentric for economists to be interested in this question. And in the case of the subsequent literature, it can be broken into two divisions. One important category of experiments study what's called numerosity discrimination. How accurately can people tell apart the numerosity of one visual array from that of another? So sometimes this involves accuracy of comparisons. The subject has to say which of two arrays has more things in it than the other one, and you look at how accurately they get that question right. Another kind of question is whether the subject can accurately recognize differences. So the question is, does the second array contain the same number of elements or a different number of elements? And you see how accurately they get that question. So these are examples of studies of the accuracy of numerosity discrimination. Another class of experiments that I want to talk about are experiments that study numerosity estimation. Here, the subject is presented with a visual array, and they have to estimate the number of items that it contains, and they do this too quickly to be able to simply count them. So rather than counting the items, they have to take a quick look at it, which is what Jevons was doing in his experiment. He used himself as the experimental subject. He tossed beans in a box and then quickly looked in the box and made an estimate of how many beans he thought had made it into the box, and then later counted them and compared that with his quick estimate. Anyway, much more sophisticated methods are used now, but there's an extensive study of accuracy and biases in numerosity estimation. Okay, so what kind of things do people find? Well, they find that the responses are random, as with comparisons. When people have to compare two numerosities, their responses are random, just as when they compare two sensory magnitudes of other kinds, so two lengths, two areas, and so on. That may not surprise you that there are random errors in people's responses. More interestingly, the probability of confusing a number n2 with another number n1 when presented as visual arrays doesn't just depend on how much the difference between n2 and n1 is. If n2 is bigger than n1 by 5, that isn't enough to tell you how likely someone is to mistakenly think that n1 is bigger than n2 when really n2 is bigger than n1 by 5. Instead, the probability of confusing n2 with n1 falls. Well, rather, it's not so maybe surprising that the probability of confusing the two numbers falls the bigger the objective difference is. But the difference required for a given accuracy of discrimination also increases the larger the numbers are. And it increases approximately in proportion to the size of the first number. That's something that in other sensory contexts is called Weber's law, the idea that the difference between two sensory magnitudes has to grow in proportion to the absolute size of the two magnitudes for the accuracy of telling them apart to remain constant. One sees something like this also in comparisons of numerosity. So here's an example of experimental data from a study by Nieder and Merton, published in 2007. What's going on here is a first visual array is presented, and then it goes away, and then a second visual array is presented. The subject has to say whether they think the second visual array has the same number of items in it or not. The curves are drawn for different true different numbers presented on the first array. So the different colors and the numbers indicated at the top of the screen indicate what number of items were presented in the first array. So the green curve furthest to the right is when the first array had 30 items in it. The light blue curve more in the middle with the 20, that's when 20 items were in the first array. On the horizontal axis is the number of items in the second array, and on the vertical axis, the fraction of the time that the subject thinks that the second array has the same number of items rather than a different number of items as the first array. Okay, so you see errors here. People do say that they have the same number of items in the array with a positive fraction of the time, even when the numbers are different. But each of these curves peaks when the number in the second array, the number on the horizontal axis, is the same as the number presented the first time, which is the number indicated by the color. So each of the different colored curves does peak when the two numbers are exactly the same. So that should reassure you. But the thing I want to point out is not just that there's random error, but that these curves get fatter as you move to the right. So if you present only 4 items in the array, then even if there are only 3 items or only 5 items, people can think they're the same number some of the time, but much less often than they say it's the same number when you present them with 4 items. So the accuracy falls, the probability of saying that they're the same falls off quite sharply when it's only 2 items or only 4 items over there at the left of the figure. When you're presenting 26 items or 28 items or 30 items, these are very fat curves. The number of items in the second array can be different by many numbers from the number of items in the first array and still have a non-trivial probability of the subject thinking they were the same. If I transform the horizontal axis, now making distances on the horizontal axis be linear in the logarithm of the second number rather than having them equally spaced on the horizontal axis, now you see that the width of each of these curves is about the same. And so that's suggesting that it's approximately the difference in the logarithms of the number of the 2 items presented that's determining how likely the subject is to confuse those 2 numerosities with each other. So that's this Weber's law idea. So that's one kind of finding about imprecision in the representation of number information in the brain that we know about. how can we explain this Weber's law relationship in terms of noisy internal representations? It gives us a particular quantitative hypothesis about that. And it's an old hypothesis. This actually goes back to work of Gustav Fechner back in the second half of the 19th century, where he proposed this explanation of Weber's law in the case of other sensory domains. And so the interpretation that Fechner proposed is, suppose you have a stimulus which has a true magnitude, which I'm going to call n, because here it's a number n. There's a true numerosity n. Suppose that stimulus results in a random pattern of mental activation in the brain of the subject. And I'm going to call that subjective representation is going to be indexed by this number r. So that's going to be the noisy internal representation of the numerosity of the visual array. The subject is going to have to produce their responses to questions about what they were shown on the basis of this noisy internal representation r. Fechner's hypothesis is, suppose R is drawn from a normal distribution. The mean of that normal distribution depends on n, but suppose it grows with the logarithm of n, not linearly with n. Suppose the mean of the distribution is the logarithm of n. The variance is some positive quantity nu star or nu squared, which is independent of n. That's Fechner's hypothesis. And suppose now the subject is going to base their judgment. Suppose you ask them, in the case of two stimuli, each has an internal representation of this kind. You ask them whether N2 was bigger in numerosity than stimulus N1. Suppose they're going to say, I think it's bigger if and only if this R2 is bigger than R1. So now we have a model, a probabilistic model of their responses. We can calculate, according to this model, the probability that the subject will say, I think N2 was bigger than N1. And as a function of what the true numerosities N2 and N1 are, the probability that R2 will be bigger than R1 under the model I just presented is given by this function, where this phi, capital Phi, is the standard, the cumulative distribution function of a standard normal distribution. And you see it depends on the difference between the logarithm of N2 and the logarithm of N1, which is the logarithm of the ratio of N2 to N1. And that's because the mean of those two distributions, that R2 and R1 are drawn from, those means are different to the extent that the logarithm of N2 is different from the logarithm of N1. The noise parameter nu is also entering there and determining the randomness of people's choices. Okay, so this model predicts that Weber's law should be true because the probability of an erroneous classification for any values of N2 and N1 depends not on the absolute difference between N2 and N1, but on the ratio of N2 to N1, or the difference in the logarithms of the two numbers, which is more or less what we seem to see. So we can hypothesize that this number information has a noisy internal representation with the particular structure proposed here, then we can make sense of those earlier data. I'm going to turn now to what we learned from experiments on numerosity estimation. We can look at whether there's not just noise in people's estimates of the numerosity of a given visual array that they're shown, but whether there's bias, whether on average they estimate the number of items to be different from what it really is. And the answer is the literature finds biases, and typically experiments of this kind find what's sometimes called a conservative bias, which is the idea that the smaller numbers presented are overestimated, while the larger numbers that are presented in the same experiment are underestimated. There's a crossover point then between numerosities that result in overestimation and the larger numerosities that result in underestimation. But this crossover point is different in different studies. And what's been observed is that the crossover point seems to be different across studies depending on the range of numerosities that are used as stimuli in a given study. For people who heard the first lecture, that shouldn't come as a complete surprise, because we saw that in other sensory domains, and it's what we were calling the central tendency of judgment. Back in lecture 1, we see exactly the same kind of thing in the case of estimates of numerosity of visual arrays. So this is an example of that from a paper by Nobile and co-authors, which is interesting for this purpose because this is a case of a study where in the same experiment, there are blocks of trials in which the range of numbers used are different, although the numbers are being presented to people in exactly the same way. It's exactly the same kind of visual arrays used in the two experiments represented in these two panels. The way the subjects report their estimate of the number is exactly the same. So everything about the experiment are the same, except that the distribution of numbers used in the left panel only vary between 1 and 30, whereas the numbers presented vary between 1 and 100 in the right panel. What you see in both experiments is this pattern of bias, where you have systematic overestimation of the lower numerosity arrays and systematic underestimation of the number of items in the higher numerosity arrays. So in the left panel, we see that the responses are on average above the diagonal over to the left, and they fall below the diagonal over to the right. We see the same thing in the right panel, but the crossover point between overestimation and underestimation is different. In the left panel, we see that you move from overestimation to underestimation for numerosities below 20. That's when the range used in the experiment only vary between 1 and 30. In the right panel, instead, we have numerosities, true numerosities on the horizontal axis, much bigger than 20, that are still being on average overestimated. The crossover point is somewhere above 50. And that's now when the range of numerosities used in the experiment vary between 1 and 100. Okay, so this is this idea of the central tendency of judgment that we talked about in the earlier lecture. And again, that kind of pattern, not just a bias, but the bias shifting depending on the distribution of values used in the experiment, is consistent with this idea of somewhat optimal responses, if we suppose that the responses have to be based on a noisy internal representation of the information presented. Okay, so we see this conservative bias, we see the central tendency of judgment. The nature of the bias is often fitted in the experimental literature by fitting a power law relationship to the relationship between the mean estimated numerosity for a given stimulus and the true numerosity. So the average value of the n hat, the subject's estimate of the number of items presented, how that's related to the true number of items presented, and is often fit to a power law like the equation here in the slide. And what is found is that this exponent beta is positive, but generally less than 1, at least a little bit less than 1. And that gives you an increasing strictly concave relationship like the one shown in that previous figure, or sometimes a log-log plot is used, and then you fit a straight line to the log-log plot. The slope of the log-log plot is then this coefficient beta, and again, it's typically found to be at least a bit less than 1. Another finding in this experimental literature on numerosity estimation is that the variability of estimated numerosity grows in proportion to increases in the true numerosity, and in particular grows in proportion to the average estimate. And this is what's sometimes called a property of scalar variability. So the variability of people's estimates of numerosity seems to scale in proportion to their average estimate of numerosity. And that's something that we also want our model of the nature of the noise in the mental representations of number information to be consistent with. Okay, so how can we understand these biases in people's estimates of numerosity? This is going to naturally follow from the hypothesis that the judgments have to be based not on an accurate mental picture of the things in the array, but a noisy internal representation of the number of items that were presented. So we have to suppose the judgment is based on a noisy internal representation R, and that this R is not itself the subject's perception of the number of items. It's instead noisy information that can be used as the basis of an estimate of what the number of items are. We could ask what an optimal rule for estimating the true number of items from this noisy pattern of mental activity is. We should expect shrinkage toward the prior mean as a consequence of having an optimal Bayesian estimate based on this noisy evidence that's present in the brain of the decision maker. That hypothesis can explain not only that there's a conservative bias, but why the crossover point should vary with the subject's prior, which should be variable depending on the range of numbers actually being used in the experiment. Can we get this not just qualitatively, but quantitatively? And the answer is yes, with a relatively simple model. Suppose we hypothesize that presenting a visual array with a true numerosity and gives rise to a noisy internal representation of the numerosity of the array. We're going to call that R. Suppose this quantity R is a draw from a normal distribution, just as in Fechner's hypothesis. R is drawn from a Gaussian distribution with a mean equal to the logarithm of the true numerosity, a variance nu squared, which is independent of the true numerosity. So we already saw that that was a hypothesis that could make sense of this Weber's law finding from the numerosity discrimination experiments. We're now going to consider its consequences for biases in numerosity estimation. So suppose our hypothesis is that the subject's estimate, n hat, is actually for a given noisy internal representation R, the subject's response n hat will be the conditional expectation of the true n conditional on this noisy internal representation R. What that conditional expectation is going to depend on their prior, or on the prior for which we're optimizing the decision rule. I'm going to assume here, to make the calculation simple, that the prior is also a log normal distribution. So the logarithm of the true numerosity is drawn from a Gaussian distribution. That's going to make the calculations simple. This theory that I'm proposing is then going to be a quantitative theory, both of what the predicted variability should be in subjects' estimates of numerosity and what the bias should be on average in their estimates of numerosity. It gives you a theory of variability and bias, both in discrimination tasks and in estimation tasks of the kind that I was just talking about. What does it predict? So I won't go through the calculations, but we can use the properties of a multivariate Gaussian distribution again, because now the log of n and R are two random variables whose joint distribution is a multivariate Gaussian distribution. We can calculate that, that conditional expectation, and we find that the average estimate n hat is predicted to be a power law function of the true numerosity n. The mean of n hat, conditional on n, should be equal to a positive quantity a times n to the beta. The predicted exponent beta depends on the values of these noise parameters, sigma squared that was measuring the degree of uncertainty in the prior, the nu squared that was measuring the degree of noise in the internal representation. The ratio of sigma squared to nu squared determines this coefficient beta. Some of you will recognize that formula for beta as the same thing that came up in a simpler model of estimation bias that I presented in the first lecture. So again, those two noise parameters are the, and in particular their ratio, are the crucial determinant of the size of the biases here. The degree to which beta is less than 1 depends on the ratio of sigma squared to nu squared. For any positive values of sigma squared and nu squared, beta should be positive but less than 1. The fact that beta is less than 1 leads to biases, and specifically this conservatism in the biases, namely the average of n hat will be bigger than n for small enough n, it'll be smaller than n for all large enough n. We can calculate the crossover point where expected value of n hat is exactly equal to n, and that crossover point in this model is predicted to be proportional to the prior mean, the mean implied by that log normal distribution for the true n. So the idea of the crossover point shifts in proportion to shifts in the average true value of the stimulus magnitude used in the experiment is, of course, Hollingworth's central tendency of judgment that is predicted by this model. We can also ask what the model predicts, not just about the average value of n hat, but about the standard deviation of n hat. And this model, based on log normal distributions, predicts that the standard deviation of the estimated numerosity n hat should grow in proportion to the mean of n hat if we fix these noise parameters, fix the sigma squared and the nu squared, but suppose that in different experiments, the mu, that was the mean of this distribution that the true numerosity or the log of true numerosity is being drawn from. If we suppose that in different experiments, the mu is different, then as we vary that mu, the standard deviation of the subject's estimates should grow exactly in proportion to changes in the mean estimate. That's this property of scalar variability that has also been observed in many experimental studies of numerosity estimation. So all of those quantitative predictions are in fact at least approximately true in experimental studies of perception of numerosity. So we're going to be interested in then hypothesizing this very particular kind of noise in internal representations of number information as a possible model of the nature of the errors in judgments about simple lotteries. Okay, so now I'm going to turn to this hypothesis of noisy encoding of information about the decision problem and what it implies about subjective valuations of simple gambles. So suppose we consider a situation where there's a decision maker. The decision maker has to choose between a risky gamble that offers a probability P of getting a positive quantity X. Otherwise, you'll get 0. Their choice is between this risky gamble and a certain outcome. The certain outcome will give them a positive quantity C with certainty. So the Mosteller-Inoji experiment that I talked about had this form. One of the Kahneman-Tversky experiments, if we just considered the choice between A and B, in the case that involved a random gain and a certain gain, also had this form. So I'm going to talk first about a simple choice of this kind. Now, suppose that the data that the subject have been told about these potential monetary gains, they've been told this monetary amount X, they've been told this monetary amount C. Suppose each of those has an imprecise mental representation rather than a perfectly precise internal representation that's going to be the basis for the decision. We're going to suppose there's an Rx, that's the internal representation of X, and RC, that's the internal representation of C. And I'm going to suppose that the nature of the noise in these two internal representations follows this Fechner-ian hypothesis. Namely, the noisy internal representation R is a draw from a Gaussian distribution, the mean of which is proportional to the logarithm of the true number that the subject was told, and the variance of which is independent of what the true number is. So we're going to suppose that both X and C have a noisy internal representation of this kind. The noise, the randomness are independent. These are going to be two independent random draws in the internal representations of those two different pieces of information. Okay, so that particular model of noisy coding implies Weber's law and those other quantitative regularities about the errors in people's perceptions, at least of numerosity of visual arrays, where this issue of imprecision in number representations has been studied particularly extensively. I'm assuming Rx and Rc are independent random variables. I'm assuming that the same parameter nu, which measures the noise in those internal representations, is determining the precision of the encoding of each of those two pieces of information. To talk about an optimal decision, it's going to matter what the prior distribution for the true data is for which we're going to optimize the decision rule. And for the calculations here, I'm going to assume that both X and C are independent draws from a log normal distribution and that it's the same log normal distribution of possible gains. And so that's going to let me use exactly the same mathematics as in my discussion of models of biases in numerosity estimation that I was just talking about. Okay, so what do we want to hypothesize about how the decision maker is going to make the decision between the random payoff and the certain payoff? Well, suppose that they have learned to use a rule that's in fact going to maximize the expected wealth of the decision maker, subject to the constraint that this decision rule has to be based on these two noisy internal representations. They have to be based on Rx and Rc rather than on the true values of the numbers X and C that the subject was told. Note that the hypothesis now is just that they're going to make the decision in a way that maximizes the expected wealth, the expected payoff they get from this choice, which is to say, it's a decision rule that assumes that the only thing that matters is how this experiment contributes to your overall lifetime wealth. We're not assuming that it depends in some nonlinear way on earnings from the experiment being segregated from the other sources of wealth of the decision maker. Under this hypothesis, an optimal rule is one that will lead the decision maker to choose the risky choice, the risky outcome, if and only if P, the probability of the non-zero outcome, times the conditional expectation of that non-zero outcome, conditional on the noisy internal representation of X, is a bigger quantity than the conditional expectation of the certain outcome C, if we take the conditional expectation of that conditioning on the noisy internal representation RC. So I need to calculate those two conditional expectations. The algebra of calculating those two conditional expectations is exactly the same as in that numerosity estimation problem that I was just talking about. You'll notice I assumed a log normal prior, just as I did in the earlier discussion. I assumed the logarithmic model of the encoding following Fechner, just as in the earlier discussion. So the same formulas for the conditional expectations of these numerical amounts, conditional on their internal representation, is going to be used. And I already told you that those conditional expectations had a particular form. It's going to make this inequality be equivalent to saying that Rx and Rc have to satisfy the inequality on the second line, which involves a quantity beta. And this beta is that same coefficient beta that came up in my discussion of biases in numerosity estimation. It depends on the ratio of the two noise parameters, the sigma squared measuring the degree of uncertainty in the prior, and the nu squared measuring the degree of noise in the internal representations. So the probability that the subject will pick the risky gamble is going to be determined by the probability that this inequality holds. And since Rx and Rc both have normal distributions, we can answer what the probability of that is using the properties of a bivariate normal distribution. Again, Rx minus Rc is normally distributed. The mean of that distribution depends on the difference in the means of the distributions of Rx and Rc. That means it depends on the difference between the log of X and the log of C. So it depends on the logarithm of the ratio of X to C. And if we ask what's the probability that Rx minus Rc is big enough for the inequality at the top of the slide to hold, the answer is the probability of that being true, which is the predicted probability of the subject picking the risky outcome over the certain one, is the function given at the bottom of the slide. Again, capital Phi is the cumulative distribution function of a standard normal distribution. We can calculate the probability of the noisy internal representations being such that it will make sense to pick the random gamble. And it's this function of the ratio of X to C. And it also depends on what the P, the probability of the non-zero outcome of the gamble was, and it depends on the nu, this parameter indexing the noise of the internal representation. It depends on that beta, and the beta depends on the ratio of sigma squared to nu. Okay, so what do we learn from this model of random choice? It predicts random choice, but it predicts something very specific about random choice. First of all, it predicts that if we fix C, the certain payoff, and we vary X, and we ask how the probability of taking the risky choice over the certain choice varies as we vary X, we get the prediction that that function should be a continuously increasing function. I showed you what Mosteller and Noji found in their experimental data for exactly that question. C was always 5 cents in all of those gambles presented to the subject in the figure I showed you earlier. X was the quantity on the horizontal axis. It was varying from a smaller amount to a larger amount. They were plotting on the vertical axis the probability or the fraction of the time that the subject took the risky choice. The prediction here is that those data, when plotted in that way, should have given you an increasing curve. What should the shape of it be? The shape of it should be a sigmoid function, flat at first for low values of X over C, more steeply increasing for X over C in the intermediate region, flat again for higher values of X over C. That's what Mosteller and Noji's graph, of course, looked like. The the theory furthermore predicts not only that you should observe random choice, at least for values of X over C that are neither extremely small nor extremely large, but it predicts where the indifference point should be. Mosteller and Noji were interested in calculating that indifference point, where it seemed that by interpolating their data, the probability of taking the risky choice was exactly 50%. We can ask what the theoretical model predicts. Phi of the argument inside the function is going to be equal to 1/2 if the argument of the function is 0. The argument of the function is 0 if the numerator of this fraction is 0. So there's a particular ratio of X to C required for that to be 0. We can then calculate then what the indifference point is, and the model predicts that the indifference point should be to the right of the point where it's a mathematically fair gamble. The gamble is a mathematically fair gamble when X is equal to C over P. X will have to be bigger than C over P for the argument of this function to be 0. Why? That's because beta is less than 1. So beta inverse is bigger than 1. So that beta inverse logarithm of P inverse is something bigger than the logarithm of 1 over P. So the numerator to be 0, the log of X over C has to be something bigger than the logarithm of 1 over P. So X over C has to be bigger than 1 over P. Okay, so we predict that the indifference point should be to the right of C over P. Thus, the model predicts apparent risk aversion if we measure risk aversion by asking where the indifference point is and comparing the indifference point to C over P. The indifference point requires X to be bigger than C over P. We would call that a measure of risk aversion, which was indeed what Mosteller and Noji were inferring from their figure. They were measuring the degree of risk aversion, asking for the von Neumann-Morgenstern utility function to be consistent with that degree of risk aversion. Okay, so we predict apparent risk aversion, even though our decision rule was optimized to maximize the mathematical expectation across different decision problems of the overall wealth of the decision maker. So we're in fact not assuming diminishing marginal utility of additional earnings from the experiment was a relative consideration in what the decision rule was optimized for. Nonetheless, we can account for apparent risk aversion. How well does the model fit quantitatively? At least qualitatively, it's like what we see in the Mosteller and Noji data. Can we fit it to those data quantitatively? And the answer is pretty well. So here I fit my two parameters, sigma and nu, to the Mosteller and Noji data. And the answer is if I pick sigma around 0.26 and nu to be around 0.07, then this predicted sigmoid function for the probability of taking the risky offer fits those data points for the fraction of times that the gamble was taken and for each value of X quite well. And it predicts that the indifference point should be at a point quite close, around 10.7 cents, quite close to the one estimated by Mosteller and Noji. Now you might say, well, okay, you have two free parameters to fit not a terribly large number of data points. Maybe that's not extremely impressive. And so you might ask, are those crazy values of the noise parameters and the uncertainty parameters that you have to assume to get that? So first of all, is it a crazy assumption that the degree of uncertainty that the subject has about what X might be on a given experimental trial should be captured by sigma equal to 0.26? Is it an amazing amount of noise in the internal representation to assume the nu should be around 0.07? What do these figures imply? The assumption of a prior in which sigma, a log normal prior in which sigma is equal to 0.26 means that the difference between the maximum and minimum values of X used in the trials that you can see reported in Mosteller and Noji's figures, the maximum and minimum values of X differ by 1.16 log points. If sigma is 0.26, that means the range of values that you see used in the experiment differ over a range of about 4.5 standard deviations under the prior. And if log X is normally distributed, expecting log X to most of the time be within about plus or minus 2 standard deviations of its mean, is what you would expect. So the fact that we see them varying, the maximum and minimum values varying between a little more than 4 standard deviations, is about what you would expect if the x's used in the experiment are in fact draws from a log normal prior with this value of sigma. So it's as if the subject's sense of their degree of uncertainty about the log of x is reasonably well calibrated to the range of values of log x actually being used in the experiment. So if we assume that sigma is fixed by the degree of uncertainty about x on each individual trial, that would be reasonable in the experiment, given how much variability in the log of x there is in the values actually presented to the subjects in the experiment, then we would have 2 separate ways of estimating what the nu has to be for the subject's data to be consistent with our model. We could estimate nu from the degree of randomness of choice, because the assumed randomness of the internal representation is used to predict randomness of choice. That means we could look at the slope of this probability of choice curve, how steep or how flat it is, and estimate nu from that. Look at its steep in that central part of the curve, its slope in the central part of the curve. Or we could estimate nu from what nu has to be to predict where the indifference point should be. Because for a given amount of prior uncertainty, nu is going to determine the predicted indifference point, the predicted degree of risk aversion. We could ask what nu has to be to fit that aspect of the experimental data. Those are quite different, in principle, logically separable aspects of the experimental data. We could estimate nu from each of them and get that nu needs to be about the same size, both to explain the steepness of the curve and to get the indifference point to be around where it is, and the same value of nu is in fact getting both of them to be about right. Okay, so under this proposed explanation for risk aversion, we now have not just an explanation for seeing risk aversion, but we can explain the Rabin paradox. It's no longer a puzzle that people would often decline even very small bets. The stakes can be very small, like they are in the Mosteller and Noji experiment, and yet people can be declining them even when the bet is somewhat better than a fair bet. They can be often declining them, and yet the same person might be willing to accept much larger risks in the case of substantially larger stakes. That's the paradox. For Rabin, if we explain risk aversion as resulting from expected utility maximization with a decreasing marginal utility of wealth, we cannot reconcile those 2 things with each other with the same utility of wealth function. The model I just presented has no trouble reconciling the 2 things with each other, because the model implies that the probability of taking the risky bet over the certain choice depends on the ratio of x to c. So a given ratio of x to c is required for a given probability of taking the risky option, but the ratio that's required is independent of how big c is. So c could be extremely small, meaning that both x and c are small, so the stakes are small, and yet still have a probability of taking the risky option that's well below 1, even when its x over c is big enough for it to be better than a fair bet. But at the same time, you could scale C up to a substantially larger quantity. Now the stakes are much larger, and it could still be the case that the probability of taking the risky bet remains well above 0, even though now the difference between the mathematical expectation of the risky outcome and the certain amount are a non-trivial amount. So we get the same ratio of x over c being predicted to be required for a given probability of choice in the case of smaller stakes and larger ones. Here I should point out that the theory only makes sense when I say larger stakes. I still mean gambles that are not so large that it wouldn't make sense to think that marginal utility for the outcome of the payoff from the experiment should be essentially constant. So we're still talking about stakes that are not life-changing outcomes for the decision maker, but we could still have some substantial range of variation in the size of the gambles and think that the theory should predict essentially scale invariance. Do we see that scale invariance? So it could explain the Rabin puzzle, and so at least in some broad terms, we see something sort of like that. With Melcaw and Zhang Li, we conduct a laboratory experiment specifically to test this more specific quantitative prediction of the model. We have an experiment like the Mosteller and Noji experiment, but our subjects are presented with a series of choices in which both X and C are different on different trials, and we present the different combinations of X and C in a randomly ordered way. But the probability P of getting the non-zero outcome X, if you take the risky option, is always 58%. So in all of our experiments, P is all the trials, P is the same. X and C are both varying from an approximately log normal distribution. And we want to ask whether the ratio of X to C required for a given probability of accepting the risky option over the certain option varies with C or not. So we have 6 different values of C ranging from as low as $5.55 up to the highest value of $31.40. Those are 6 approximately equally spaced increments in terms of the logarithm of C, so that we can look at the consequences of this logarithmic model of coding. And here's what our data look like. So in the upper panel, I'm presenting a plot like the Mosteller and Noji plot. The value of X is again on the horizontal axis. The vertical axis is the fraction of the time that subjects take the risky bet over the certain amount. And the 6 different curves with the 6 different colors correspond to those 6 different values of C. So the darkest blue is that lowest value of C. C is $5.55. The lightest pink over at the right is the highest value of C. C is now $31 and some. Okay, and so what you see is for each value of C, we get an increasing but sigmoid shaped curve, as Mosteller and Noji did. But now as I vary C, instead of one such curve, we get 6 curves for the different values of C. As you vary C, the curves shift over to the right. That, of course, makes sense. The value for a higher certain payoff that's available, the amount that you can earn from the risky gamble X has to get correspondingly larger for people to be indifferent between the risky bet and C. And okay, so that makes sense. A more interesting thing about the figure is if I now rescale the horizontal axis, and on the horizontal axis have X plotted in log units. So these are the same data in the bottom as at the top, but now the horizontal axis is a log scale. Now we have our 6 increasing psychometric functions, but now you notice that the 6 functions all look a lot like a horizontal translation of a similar curve with a similar degree of horizontal translation for each successive increase in C. And here's where the fact that the increases in C were approximately equal increases in the log of C comes in. As we increase C by a given percentage amount, the same percentage further increase in C seems to be shifting the curve to the right when we plot the curve against log of X, and increasing it by the same amount if each time log of C is increased by a given amount. That kind of horizontal translation and horizontal translation proportional to the increase in the log of C is exactly what that quantitative model earlier predicted. Here's if we plot the data not as a function of log X, but log of X over C. Now you see the 6 curves in the top panel. We're again plotting the 6 curves separately. The 6 curves pretty much all fall on top of each other. And if we estimate a single curve, the black curve at the bottom, that looks a lot like, that fits all of the data reasonably well. That single black curve is, of course, what the model that I presented before would predict. In the paper, we have a lot of statistical model fit statistics to show how well the model are consistent for almost all of our subjects with this hypothesis of scale invariance implied by the model of noisy coding that I presented before. Okay, so those are some aspects of the model's predictions that seem to fit pretty well. Some other implications of this model of risk attitudes that I'm going to talk about more briefly. If we consider instead a choice between a loss of size X that you can get with a probability of P or having a certain loss of size C, we can use the same model to predict the subject's behavior in that kind of choice problem where they compare a random loss or a certain loss. Which one do they want? If we suppose again that the X and C have to be encoded with noise, we have them encoded with exactly the same Fechterian model of the noisy internal representation of these quantities, although now the quantities are losses rather than gains, then I can use exactly the same calculation and I get the same formula as above, but that formula will now be the probability of choosing the certain loss over the risky loss rather than the probability of choosing the risky gamble over the risky gain over the certain gain. And the fact that that same function, once I change it into, not only change gain into loss, but I change it from accept the risky outcome to accept the certain outcome, it means that when we flip from gains to losses, the model now predicts that the indifference point should be located relative to the mathematically fair gamble in a position that implies that the subject should look like they're risk-seeking in the case of the comparison of the random loss to the certain loss. That's, of course, what the Kahneman-Tversky experiment that I talked about at the beginning of the lecture implied, that in two cases where A and B had the same mathematical expectation, when it was comparing the certain gain to the risky gain, they looked risk averse, at least the majority of subjects made the risk averse choice, but when it was risky loss compared to certain loss involving the same numbers about the size of certain loss and risky loss, the typical subject was instead risk-seeking. That's exactly what this model would imply if I assume exactly the same hypotheses about the nature of the noisy internal representations of the monetary amounts, both in the gain case and the loss case. I again assume the decision rule that the subject has learned is the one that would be optimal for them in the sense of maximizing their overall financial wealth. So it's the same exact hypothesis used to explain both kinds of behavior. Suppose I consider a more complicated problem, again motivated by that experiment of Kahneman and Tversky, where the nature of the decision problem is first the decision maker receives a transfer of size y, and they get that regardless of what they choose. They get the transfer of size y, then they have to choose between two choices A and B. A is going to allow them a risky gain, B a certain gain, or they may choose between A, a risky loss, and B, a certain loss. The model that I've just proposed, if we suppose that now the quantity Y is also subject to a noisy internal representation, the noise in that internal representation is independent of the noise in the other two internal representations of the quantities X and C, we can again ask what the optimal decision rule is. The optimal decision rule will be independent of the noisy internal representation of Y, because what the size of Y is will be irrelevant for asking which of the choices is more likely to maximize the total financial wealth of the decision maker. So we will get the prediction that the probability of choosing the risky outcome over the certain outcome when the subject has to choose A over B in the second choice will be a probability which is independent of the value of Y. That's like the isolation effect that Kahneman and Tversky hypothesized. In other words, we get a prediction that the probability of taking A over B depends on these risky gains and losses when they choose between A and B. It's independent of the size of that initial transfer. The model can predict then opposite choices in the two Kahneman and Tversky problems that I presented earlier, despite the fact that the two problems involve a choice between two identical probability distributions for final wealth. What's some further evidence that's consistent with the view that what's going on in these choices involves departures from risk neutrality that are due to noise in these internal mental representations of the monetary payoffs? But one thing we can do is I said the same parameter, the degree of noise in the internal representation in the proposed model should explain both the noisiness of the subject's choices, the fact that they don't always pick the same way when presented with a given choice problem, and the degree of apparent risk aversion, the location of their indifference point. And we can ask then whether that connection between the two things, noisiness of choice and the degree of apparent risk aversion, in fact go together when we look not at the pooled data, which I showed you before, but fit curves of this kind for each individual subject. And so we do that. We fit this sigmoid curve to the data of each of our individual subjects, letting the steepness of the curve and the location of the indifference point be independent parameters in the estimated curves for each of the individual subjects, and ask whether more noisy choice, a flatter curve, does go with more risk-averse choice in terms of the location of where the curve crosses the 50% probability or not. We do find a clear positive correlation. So this is the plot from our paper in the Review of Economic Studies. The vertical axis is the measure of risk aversion determined by the measured indifference point for each of the circles. Each of these confidence regions are the estimates from the data of the individual subjects. On the vertical axis, that dotted horizontal line indicates the level on the vertical axis that corresponds to risk neutrality. Being below it is risk aversion. Above it would be risk seeking. The further you are below it, the more apparently risk averse you are. On the horizontal axis, we have the measure of the steepness or flatness of the choice curve of the individual subject. A higher value of this parameter gamma of the estimated choice curve means more predictable choice. Lower value of gamma means more random choice. And so what you see is that the subjects who have more random choice, or further to the left of the figure, are on average also more risk averse in the sense of having a lower value on the vertical axis. The subjects who have more predictable choice, further to the right of the figure, are also closer to risk neutrality. So we do see the positive relationship, and in particular, that dashed line that's drawn there is the prediction of the model if we fixed sigma at the level of prior uncertainty that would make sense in the experiment, and assume that all of the variation in subjects' behavior was simply due to different amounts of mental imprecision of the different number representation of the different subjects. They should fall on that dashed line, and the different confidence regions for the different subjects are not extremely far away from falling on that line. Now, there is some other differences between subjects that might be interpreted as, in fact, some degree of difference in their priors, for example, but there's some degree of consistency with this prediction. There's an interesting extension of this by Manuel Garcia in his dissertation work at the University of Zurich. He has a recent paper that replicates our results in that regard. He gets a similar plot as the one that I've shown you. The interesting thing about his work is that he also shows that both the degree of noisiness of subjects' choice between these lotteries and their apparent degree of risk aversion when choosing between the lotteries is correlated with individual subjects' degree of imprecision in mental representations of number information, where he measures that from a numerosity comparison experiment like the ones I talked about back at the beginning of the lecture. So he actually has the same subjects do numerosity comparisons and choose between certain amounts and random amounts. And he shows that the estimated noise parameter, the measure of their imprecision in number representation, purely based on their ability to accurately judge the relative numerosity of two visual arrays, does correlate both with the noisiness of their choice when choosing between lotteries and the degree of apparent risk aversion in their choice when choosing between lotteries. And so that's also consistent with this line of explanation. Risk aversion in laboratory experiments varies with things that should be expected to decrease the capacity for precise representation of numbers, things like distraction of the subjects, requiring them to keep other numbers in their mind at the same time as they make the choices between lotteries, have been shown experimentally to affect measured risk aversion in a way that would be consistent with this hypothesis. If we think the parameter nu can be increased by increasing the cognitive load on the subjects. Finally, there's a recent paper by Carey Friedman and Lawrence Jan showing that sensitivity of lottery choice to this ratio of X over C can be increased by narrowing the range of monetary amounts used in the experiment. That should change the prior. Evidently, the precision of the encoding of these amounts changes when you change the tightness or wideness of the prior that the subject have about the numerical amounts that have to be encoded. That's something I also talked about back in lecture 1, and there's evidence for that kind of prior dependence of the noise in the encoding. Also in this context, I'm running out of time to talk about it, but that's also evidence consistent with this general explanation. Okay, so to sum up, a variety of different aspects of measured risk attitudes, I think, can all be explained by a unified model and using methods that are similar to ones that are commonly used to explain biases in perceptual judgments, including biases in judgments about numerosity of visual array, which might involve an aspect of the precision of mental representations very closely related to the one that's needed in decisions about monetary amounts. I think this suggests that some aspects, at least, of risk attitudes for relatively small gambles are better viewed as a sort of perceptual bias, as resulting from imprecision in people's mental representation of the terms of the problem they're presented with, rather than being an aspect of their true preferences. As in perceptual domains, an implication of this is that it's important to model the variability of people's responses and their average bias in their responses jointly, as I've illustrated in the study that I was just talking about. Often in the experimental economics literature, people treat this issue of biases and the issue of noise in people's responses as unrelated things. They study one thing without maybe even reporting the other one. They use separate parameters to fit these different aspects of the data. The results I've showed you should lead you to think that it might be important to model these two things together. Finally, the nature of the imprecision in the internal representation of monetary payoffs seems to be similar to the imprecision that's observed in people's mental representations of numerical magnitudes in other contexts. And so I think that's an important way that we can use results from cognitive psychology and other domains to discipline quantitative specifications of models of economic decision making. Thanks.
Thank you, Professor Woodford, for such an insightful talk. Very quickly, I think we can take one question from the audience. So please mute yourself and you can ask the question if anyone has any questions. Yes, please, Professor Das.
Yeah. Hi, Michael. I have a question about, it's not related directly to, so it's a more broad question in the sense that imagine that, so I have these two alternative ways of looking at things. One is that it's the risk preference. The other one is, as you say, basically it's cognitive inability to process information. Now, as a policymaker, when I'm looking at, risk preferences play an important role when I'm designing policies and so on. So is there any obvious way when, whether I'm looking at it as a preference or as a bias towards, my, inability to process information, cognitive imperfection or imprecision?
Yes, well, I think this does matter because, I've proposed a model of these choices, at least in the case of these relatively small gambles, which implies that people learn a decision rule, which is good for them. It's working for them in terms of, on average, achieving the best outcome for what is being postulated to be their true objective. And so there is an objective of and a true preference of the decision maker that you can infer from this model. If you think this model is on the right track, then by explaining their behavior, you can in fact infer what their true preferences are. And it would be a mistake to interpret then these risk attitudes as reflecting a different kind of preferences. You would be misjudging what the true thing is that the people in their behavior are learning to optimize their behavior to actually achieve. And I think that should be relevant then to welfare judgments. It implies that if you took measures of risk aversion, say fitted to these experimental data, included that that was the true degree of risk aversion of the person, and then made welfare judgments about subjecting them to more or less risk, on the basis of that inferred risk aversion, I think you could be making a mistake about what the person themselves really care about in the sense that their own personal behavior has been learned over time to optimize a different objective for them. So I think it is, in fact, relevant to welfare comparisons. And I think that perhaps common methods of estimating risk aversion to then plug into welfare calculations by taking things like financial asset prices to infer what people's true risk attitudes are, may be making big mistakes.
Okay, so there's a huge, policy implication, and you have to look at policies differently depending on which one you think is correct, right? So that's
I think that's right.
That's it. Thank you.
Thank you, Professor Woodford. I request all the participants to reserve their questions for the breakout session at 10:30 p.m. today. And also the third lecture of the series is scheduled at 8:30 p.m. So please do join us for that. Thank you so much.
Thanks.
Swati, we stay here, right? We kind of, so it's half an hour. So we stay logged in. I mean, we can
take a break as well.
It's the same link, I suppose. It's the same link. So even if we leave, we can come back through this, right?
Yes, it's the same
link. The same link will work. You can come after.
Okay. All right.
You can leave the meeting and join with the same link.
Okay.
See you all in half an hour. Thanks, Professor.
Okay.
Hi, Michael.
Hi, do you hear me?
Yes, I can hear you. So you must be a bit tired, I guess.
Okay, now I have the screen on too.
No, I mean, you must be tired, I guess. After 1.5 hour lectures, then another 1.5 hour.
Yes, yeah.
Did you have good rest yesterday night?
Yeah, okay, yes. So it's,
Okay.
given the difference in the time zones, it's hard to fit, your day and my day together. So
Yeah.
managing.
Actually, we try to find different permutation combination of timing, so that could actually suit most of the participants, come up with some kind of intersections in this.
So is this the first time that you do it online, or did you?
No, the last year
also online last year.
Yes, it was last year. It was also online. I think last year from your university, Martin Urubi delivered 3 lectures, and from Harvard, Paul and Thrush.
Okay.
They did. Actually planned to hold on, of course, face-to-face mode, and they agreed before. But meanwhile, everything went mass.
Yeah.
So how's the situation now in US?
Well, I mean, it's currently getting worse. We keep having these alternations between periods when things look like they're getting better and then they get worse again. And so right now it's in a phase of getting worse, but I mean, it's not as bad as it has been in the worst time, particularly for New York. I mean, New York, the beginning of the pandemic, the spring of 2020 was very bad. I mean, New York was one of the places in the world that was most hit then. And it's certainly nothing like as bad and as scary as that again. I mean,
so how is the impact of Omicron so far? Is it with severe Omicron?
Well, we don't know really in the U.S. I mean, it's in the U.S., but most of the evidence on exactly how fast it spreads and how severe it is, we're looking at other countries and where they have observed it more, and so everybody's nervous about it in the U.S., but it's a little too soon to know exactly what it's going to do in the U.S. We know there are reported cases, but not a extremely large number yet of Omicron cases at least that are known. I mean, the US is not as accurate in its testing as some other countries are. And, so there are other countries that maybe know more about how much Omicron they have than we do. But at the moment, we don't know a whole lot about US data on Omicron. We know there are some patients, that have it, and everybody's watching the news very nervously. Every day there's new news about Omicron, and we're very anxious about each new report about more information.
So do you go to the university? Or is it a compulsory or?
Yes. So the classes are now all in person, and that's been true since September. Since September, we've been having our classes in person, and the students wear masks in the classroom. Everyone has to be vaccinated, the faculty and the students and the staff. Everyone who comes to campus has to be vaccinated. They have to do COVID tests at certain intervals. And there are restrictions on having people who are not affiliated with the university on campus is very restricted. There are restrictions on things like eating food together and things, there are many rules that restrict what we do, but classes are being held in person.
Oh, okay. Well, so we are now 8:30. Shomendu, are you there? Shall we start? Okay. Let's start. Otherwise, it will be a bit late for Indian audience as well. So, welcome you back to the third lectures of Professor Woodford. This lecture is obviously in continuation of the previous two lectures. Just to recap, the first lectures, basically he tried to show how in a risky environment, how human brain process, and that we're trying to be modeled using experimental results. And then in the second lectures, he tried to show that, in this kind of model, so basically he talked about some kind of imprecision decisions, and it may actually produce the biased results, and more important that it could also produce a significant loss. So now, of course, we are very much eager to see how the valuation is going to be shaping up, in this kind of environment. So that will actually take us to see what kind of policies or who actually policymakers, how policymakers could design policies so that losses could be, shape up something like that. So maybe you can start, and of course for the audience, you can post your questions, clarificatory questions, and Michael, you can keep maybe a few minutes if it is possible at the end. At least we'd like to hear something, what kind of policy instrument could be used to be monitor this kind of losses, something like that. So that would be very much interesting. So now, Michael, virtual floor is yours now.
Okay, thank you all for listening. Let me see. Okay, here we go. So what we've been talking about in the previous two lectures is, at least one of the main points that has come up several times, is the idea that a consequence of supposing that decisions are based on noisy internal representations of the features or the choice options that the decision maker is presented with is that choices should be based on biased subjective valuations of the value of those options to the decision maker, and hence choices themselves should be biased by the noise in this internal representation. And that's true even under the hypothesis that the decision maker does learn a choice rule that's optimal for them in the sense of maximizing expected utility across a probability distribution of possible choice problems, subject to the constraint that their choice rule has to take as its input this internal representation rather than the true description of the decision problem. So we've seen that this, in principle, can be an important source of bias in the valuations that are determining people's choices. But a question that some of you might have had about the analyses I'm presenting is there really a reason to interpret people's choices as being based on biased valuations, as opposed to assuming that their true preferences are simply maybe something different than what you, the economic theorist, thought their preferences ought to be? Can we explain what they're doing as, in fact, simply choosing the thing that is valued more, at least choosing more often the thing that's valued more according to their true preferences? So in the application to choices between simple lotteries that I was talking about in lecture 2, you may have noticed, it was a model that implied that people would value lotteries on average in a way that is different from what the model was assuming was the true objective, the true value of that outcome to the under the true objective of the decision maker. But the theory was also one that implied that there was a probability distribution of these subjective valuations for a given lottery that was simply a function of the true characteristics of the lottery. And you might say, why am I saying that those subjective valuations are biased? They're on average different from how the decision maker really values or should value that lottery. Why don't we just say that the average value of that distribution is really how the decision maker values that kind of lottery, and they're really basing their decision on their true valuation of the lottery plus some random noise. And so we need to introduce random noise to explain the randomness in observed choice, but perhaps we just need a model where people add random noise to their true to their true valuations? Can we really tell that it makes sense to think of these valuations as involving biases, as I was supposing? So there's a particularly compelling type of evidence that suggests the existence of valuation biases. And this involves not looking at what the subject chooses in some particular decision problem, but observing the same person's choices from different choice sets and observing that what they choose in these different choice sets can't be reconciled with any coherent preference ordering, at least not reconciled with any coherent preference ordering, on the assumption that the value attached to a given item, or the value attached to a given outcome or probability distribution of outcomes should depend only on what the decision maker gets if they choose that item. And that this valuation should be independent of the context in which the item is chosen. For example, other items in the choice set that were not chosen should be irrelevant for determining the value to the decision maker of the thing that they do choose. And so this idea, of course, is a familiar one. It's the one behind what are called axioms of revealed preference that identify features of consistency between the choices from different choice sets that would have to be satisfied for there to exist a coherent preference ordering behind those choices. Familiar one that I'm sure everyone is familiar with is the axiom that choices should satisfy transitivity. If you observe out of a choice set between the choices A and B, the decision maker always definitely chooses A, and out of the choice between B and C, they always definitely choose B, then it cannot be observed, in order to satisfy this axiom, it cannot be observed if you present the same decision maker with a choice between A and C, that they pick C over A. Because to explain the first choice of A over B, you have to assume they value A more than B. To assume the choice of B over C, when the choice set is B and C, you have to assume they value B more than they value C. If that's true, they must value A then more than they value C. So they couldn't pick C instead of A if presented with the choice set A and C. So that's a way that by comparing choices in several different choice problems, one can look for evidence of inconsistency with a coherent preference ordering. And if one observed instead of violation, one might well conclude that what's going on is that these subjective valuations are in fact context dependent. So we could reconcile the existence of a cycle of the kind I was just describing by the fact that maybe A looks better to the decision maker when they're comparing A to B than when they're comparing A to C, even though A gives them the same things in both cases. Maybe it looks better when you compare it to B than when you compare it to C. And that would explain the fact that they choose A over B, but they don't choose A over C. Or similarly, we might hypothesize maybe B looks better when you compare it to C than B looks when you compare it to A. That's why B isn't chosen when the choice is between A and B, but B is chosen when the choice is between B and C, even though C would be chosen over A, and so on. So if valuations are context dependent, that would be an explanation for these kinds of violations of axioms like transitivity. Now, a problem that you may immediately recognize with saying, okay, we're going to look for violations of transitivity, for example, to show that valuations are context dependent, is that we've already talked back in the first lecture, and again last time, that choice observed in experimental situations, even in very simple choice problems, appears to have a random element. Given that, an apparent inconsistency among the choices made on some small number of individual occasions wouldn't have to mean that each of these individual items doesn't have a context-independent valuation. It might just be that that valuation is random in the way, say, postulated by the additive random utility model that I talked about back at the beginning of lecture 1. So the idea is A, B, and C could each have a value to the decision maker. It could be quite well defined. It could be independent of what the choice set is. but they, instead of comparing the value of A to the value of B, they compare the value of A plus random noise to the value of B plus random noise. And it might happen that on 3 particular occasions, given what the random noise happened to be, that they picked A over B on one occasion, they picked B over C on one occasion, they picked C over A on one occasion. It's because the random noise was different on these different occasions. But we can formulate tests of consistency with the hypothesis of context-independent valuation that would apply even in the case of a random utility model of that kind. And so I want to talk a little bit about that, and then some experimental evidence of violation of these requirements. So suppose we consider any choice model according to which for any outcome, any option you can choose represented with an outcome that's represented by some vector boldface X. So the X is in boldface because it may be a vector specifying outcomes in different states of the world or various different attributes of the thing that you're choosing. And there's a valuation function, the V of X, which is going to define a definite value for that thing to the decision maker as a function of that complete description of the outcomes you get by choosing that option. And suppose then that our model of choice is that whenever the decision maker can choose between the set of options in some choice set, capital C, they're going to pick the option that maximizes V of X plus epsilon, where there's a boldface X now for each of the choice options. Little c, there's a random epsilon drawn for each of the choice options. Little c, for a given draw of those random noise terms, we pick the element in the choice set that maximizes the sum of these two things. We suppose furthermore that those epsilons are IID draws from the same distribution for each of the choice options. In the case that this is true, then there are a couple of requirements that I want to talk about that the decision makers observed choices should have to satisfy. One is a generalization of that requirement of transitivity that I just referred to. Now it becomes stochastic transitivity. So it's not that if you ever observe A chosen over B and you ever observe B chosen over C, then you can never observe C chosen over A. But one can still say that if option A is chosen more often than not when the choice set is A and B, and B is chosen more often than not when the choice set is B and C, then it can't be true that C is chosen more often than not when the choice is between A and C. They must choose A more often than they choose C, although the choice could be probabilistic in each of the three cases. Okay, so you can show that the random utility model with context-independent valuations for the three options would still have to satisfy stochastic transitivity. Because if they choose A more often than not when the choice set is A and B, then under the hypothesis on this slide, that means V of A is bigger than V of B. If they choose B more often than not when the choice set is B and C, that would require that V of B is bigger than V of C. And if V of A is bigger than V of B and V of B is bigger than V of C, and those valuations are context independent, then V of A has to be bigger than V of C. And so when the choice set is A and C, since V of A is bigger than V of C, even when you take into account the random terms, you must more often choose A than C, even though some of the time you could choose C. Okay, so that's the requirement of stochastic transitivity, and that can still be tested experimentally with a large enough observations to observe how frequently each item is chosen out of a given choice set, although you can't test it by just presenting each of the choices once. Another axiom that would be implied, that would be required for this kind of choice model to be right, is what's sometimes called the axiom of regularity. And this is the assumption that if you have a choice set and you add an additional option to the choice set, adding an additional option to the choice set can never increase the probability that the decision maker chooses one of the options that was already in the smaller choice set. So if you have a choice set A and B, and you observe that the decision maker chooses A only 30% of the time, if you add another option C, and say the choice set is now A, B, and C, they cannot choose A more than 30% of the time when you add that additional option. And the reason is because according to the model, they would only choose A if the value of A plus the random term epsilon for good A turns out to be bigger than V plus epsilon for each of the other two offered options. And that can't be more times than the number of times on which V plus epsilon for option A is bigger than V plus epsilon for option B if you completely ignored the other option. Okay, so this axiom of regularity, again, is something that can be tested. In fact, we find experimental violations of both of these two axioms, stochastic transitivity and regularity. I want to talk about some examples. So on the issue of stochastic transitivity, one famous early discussion of this was published in Econometrica back in 1954, an article on transitivity of preferences by May. So he conducts an experiment where college students, who are the experimental subjects, are presented with a series of questions about hypothetical spouses, and they're told about the characteristics of the hypothetical people on each of three dimensions: intelligence, appearance, and wealth of the family that the person is from. But in the experiment, they're not told the characteristics of these three hypothetical people, X, Y, and Z. In each choice problem, they're only presented with the description of two of them. So say X and Y, and ask which you would like. What you notice is that each of the three hypothetical people is best on one of the options and is also worse on one of the options. So X is being described as very intelligent, whereas Y and Z are only intelligent or fairly intelligent. But X is also worse on appearance. X is described as plain looking, whereas Z is good looking, and Y is described as very good looking. Okay, so in fact, we've constructed the example. So each of the hypothetical people has one of these dimensions is their strongest point, and they're stronger than the other two, and one of them is their worst point, and they're worse than the other two, and one of them is a dimension on which they're intermediate between the other two. The question is whether the choices observed are going to satisfy the hypothesis of transitivity or not. So out of these 62 subjects, 45 of them did report choices when asked about X versus Y, Y versus Z, X versus Z. They reported orderings that did satisfy transitivity. 21 of them, so about a third of the total sample, made a choice as if they were simply ranking the potential spouse on intelligence and ignoring the other dimensions. But the interesting thing is that a non-trivial number do report orderings that are not transitive. 17 out of the 62 do report orderings between those three choices that are not mutually consistent with any transitive ranking of the three people. And the interesting thing is not just that some people report choices that don't satisfy transitivity, because a random element in the choice could account for that, but that all 17 of the ones that report preferences that imply a cycle are the same cycle. What I call here on the slide a majority rule cycle. All 17 of them said they preferred X to Y when presented with the choice of X versus Y. They preferred Y to Z when presented with the choice between Y and Z, and they preferred Z to X when presented with a choice between X and Z. And so that is inconsistent with transitivity. It implies a cycle. Interestingly, all 17 of them, the cycle went the same way. And so saying that it's just because there was a random draw on each given trial, modifying their assessment of the value of marrying any of these people, makes it puzzling that you would not just get violation of transitivity, but always in the same direction. There's a simple hypothesis about what's going on, which I refer to when I call it a majority rule cycle. The 17 who had apparently cyclical preferences all were making choices in a way consistent with a simple heuristic, which is you consider the three attributes and ask, suppose each attribute gets a vote, and ask on which of the two options is better on the majority of the attributes, which one is better on at least 2 out of the 3 attributes. And the answer is when you compare X to Y, X is better on 2 attributes than Y, but worse on 1. So X is very intelligent, so better on the intelligence attribute than Y. X is better on wealth from a well-off family as opposed to a poor family, so better on both of those attributes, but X is worse than Y on appearance. X is plain looking, whereas Y is very good looking. But if you simply count number of attributes on which X is better than Y, majority rule says prefer X over Y because X is better on 2 attributes, only worse on 1. But Y is also better than Z on 2 attributes, only worse on 1. Z is also better than X on 2 attributes, only worse on 1. If you ask how is that possible, that's actually a famous paradox of voting that Condorcet discovered back in the 18th century, that if you rank, if you have the outcome of an election determined by majority rule, you could compare 3 different candidates to each other in a head-to-head vote and have a cycle, have majority rule produce a cycle. Candidate X is preferred to candidate Y is preferred by a majority to candidate Z is preferred by a majority to candidate X. That's what would be going on if this individual decision maker were making their decisions on the basis of this majority rule heuristic, but that's not consistent with any well-defined preference ordering, which values each of these options simply as a function of the characteristics of that option itself. Okay, similar violations of stochastic transitivity have been found since then. There's a fairly large literature on this, and it's often reported that in problems with the structure of May's problem, that the subjects who exhibit cyclical preferences typically exhibit cycles in accordance with the majority rule heuristic, seldom the cycle in the opposite direction. There's this more recent survey paper by Zhang and co-authors reviews the literature on this. And that's a puzzle, since if the cycles were occurring simply because of adding a random term, an independent random term, to each of the valuations, you should be able to produce cycles in the opposite direction to the majority rule heuristic, as in the same direction as the majority rule heuristic equally often. Okay, I also mentioned an axiom of regularity. Violations of the axiom of regularity have also been discussed for decades. They're fairly well established experimentally. A classic example of violation of the regularity axiom involves what are sometimes called decoy effects. So the idea is you have 2 goods, adding a 3rd good to the choice set can increase the likelihood of choosing one of the 2 original goods relative to what would be the case if only the first 2 options were available. The 3rd good is called a decoy because the idea is that a marketer could add it to the choice set, not because they expect customers to be interested in buying the 3rd good, but simply because it's going to distract the attention in some way of the customers in a way that increases purchases of one of the other goods. And so there have been experiments demonstrating this for decades. A particularly well-known example of a decoy effect affecting choice in a way that violates the regularity axiom is what's sometimes called the asymmetric dominance effect. That was first discussed in a paper by Huber, Payne, and Puto back in 1982. Since then, there's been a very extensive experimental literature, particularly among students of marketing. Heath and Chatterjee have a review paper reviewing that literature back in 1995. There was already a very extensive literature to review in 1995, and there's been a lot of subsequent literature as well. The idea, the asymmetric dominance effect, is the idea that if you have 2 options, they differ on at least 2 dimensions, and neither of the 2 original options dominates the other. So one is stronger on one dimension, the other is stronger on the other dimension. Say one is better in quality, but the other one is lower in price, although also lower in quality. So one is better on the quality dimension, the other is better on the inexpensiveness dimension. Adding a decoy that's dominated by one of those options, but not by the other of the original options, increases purchases of the option that dominates the decoy. So you had originally a cheaper item but lower quality, a more expensive item that was higher in quality. Many consumers go for one, many consumers go for the other, introducing a decoy which is both even more expensive than the previous expensive option, but not much better in quality than the previous expensive option. makes the previous expensive option more attractive. So it can increase purchases of that good, even though that good was always available. So apparently what seems to be going on is that the presence of this decoy good makes the one that dominates the decoy look better. And this is something that's well understood by marketers. It's discussed even from a practical point of view, like this paper by Itamar Simonson in a management review is addressed to people in marketing about how to understand their customers and use ideas of this kind to increase their sales. Okay, so there are a variety of explanations for effects like that. I think it's interesting to observe that it doesn't depend on a setting where you have people shopping in a shop and they can understand that the manager of the shop has chosen to put certain things on the shelf and other things not, and they may be drawing assumptions about the nature of those things from the fact that a particular shop has put particular things on the shelf together. I'm not sure one needs to think that inferences about such a complex setting like that are what are really going on here. Paolo Nottinson has a recent paper in the Journal of Political Economy that shows that, that points out that similar phenomena are also observed in animal behavior. And I think that suggests that there might be something pretty basic about perceptual processing of the world that shows up very commonly, given that we see very similar phenomena in animal behavior as this kind of decoy effect in marketing to humans. So this is an experimental study that that Nottinson talks about. It was actually published by Lee and Ryan in Science magazine. The experimental subject is that frog in the upper left, the so-called Tungara frog. And the experimental setting is shown in the two pictures. I don't know how well you can see them. There are two versions of the experiment. A and B are two different versions of the experiment. In each case, the experimental subject is a female frog placed on the floor in this room, and there are 3 speakers in the room. And sounds are played through the speakers, which are recordings of male frogs' mating calls. And so the question is, which of these mating calls is going to be more interesting to the frog, that's the experimental subject? They're going to observe where she hops, whether she hops over toward one of the speakers because she's interested in that sound or a different one. And so we're going to assume this means one mating cry is more attractive than the others to this frog. The different mating cries vary on these 2 dimensions as shown down in the lower left. There's an A and a B and a C. It can be verified experimentally that more of dimension 1 makes the mating cry more attractive to the frogs. More of dimension 2 makes the mating cry more attractive to frogs as well. A and B are chosen so that each of them is better on one of those 2 dimensions, and there's not a strong preference in the experimental subjects between A and B when A and B are the 2 choices. C, labeled here as the decoy, is another possible mating cry, which has been constructed so that it's really bad on dimension 2. It's not too much better, though, on dimension 1 than at least than option A. And so that's the decoy, which is not quite dominated, but comes close to being asymmetrically dominated. It's almost dominated by A, the so-called target. It's not dominated by B, though, because it's definitely better than B on 1 dimension. Okay, so that's the structure, the setup. The 3 speakers play the 3 sounds. In the first version of the experiment, the 3 speakers are on the floor, and so the frog could go over to listen to either of them. In the second experimental design, one of the speakers is up on the ceiling. The clever thing about this is it means the frog can only choose one of the other 2, but we can ask whether the presence of that other sound, she's hearing that other mating cry, although it's up on the ceiling and she can't possibly go up there, whether that has any effect on choice between the other 2. Okay, so here are the data over on the upper right of the slide. The data is indicating probabilities of choosing A, B, or C in the case of different menus. So the first line where it says the menu is A and B, that means only the 2 sounds A and B are played, and you see what the frog chooses. They choose B more often than A, but they still choose A not quite 40% of the time, but definitely more than a third of the time. So substantial choice of A as well as B, although a little preference for B apparently. When C is compared just to B or C is compared just to A, either A or B are preferred a strong majority of the time over option C. So option C is not that interesting in binary comparisons. Now, the interesting question is, what if you add C when A and B are also present? So the next to last line of the table, A, B, C, all three sounds are being played and they're all speakers on the floor. So all three choices are possible. The interesting thing is now when C is also there, not very many times does the subject actually go over to listen to the speaker is playing option C, but they go to option A more often than when the choices were only A and B. So if the choices are only A and B, they only go to option A 37% of the time. When the choice set is expanded to A, B, and C, now they go to A 55% of the time. And if it's A, B, and C is heard, but C is up on the ceiling, that's what A, B, and C with a slash through it means. C is not available, but it's audible to the subject. Now they go to A 61% of the time. So the extent to which the choice of A over B, when only A and B are the options that are available, goes up quite a lot when they can hear sound C, although they can't choose it. Okay, so that's a puzzle from the point of view of this axiom of regularity being satisfied. And Lee and Ryan, in fact, who are biologists, are interested in that. They say that this is evidence of irrationality in the way that frogs make their mating choices, which they're interested in because they think evolution should have favored some rational decision rule. There should be something about the different mating cries that imply a greater degree of biological fitness of mating with one kind of frog rather than another, and they wonder why evolution has not led to a decision rule pattern of behavior that would in fact satisfy these axioms of rational choice. Okay, so demonstrations of these kind of context effects often assert that people's choices, or frogs' choices in this case, are being shown to be irrational. And sometimes people think that means the whole idea that people have any kind of coherent preferences behind what they're doing has to be rejected. But one might wonder, if these patterns of choice aren't serving any coherent objective, why would there be such characteristic patterns that can be replicated many times in many different experiments? The alternative view I want to explore here is that these are further examples of choices being based on biased valuations, but where the biases in these subjective valuations can be understood as ones that are optimal. They follow from optimal Bayesian estimates of what the value of the alternative options to the decision maker are. In the case of the frog, it would be an optimal Bayesian estimate of the fitness value of mating with someone who produces that particular mating cry. That these can be optimal Bayesian estimates of the alternative options, given that the estimate has to be based on a noisy internal representation of the features of the available choices. And so that's what we want to pursue. Now, you might think that when we introduce this hypothesis of optimal decision making based on an imprecise internal representations, you're not going to get any reason to violate those axioms of stochastic transitivity or regularity. And in fact, you might not. I mean, if we assume that the vector of characteristics boldface X is encoded by some vector boldface R, some multidimensional internal representation, and we have a probability distribution for R conditional on X, which depends on the vector of characteristics X, but is independent of the identity and the characteristics of the other options in the choice set. And you furthermore assume a prior over the possible choice situations where under the prior, the distribution of possible values of the vector X is also independent of the identity and characteristics of the other options in the choice set. Then you would get the prediction that there should be an optimal Bayesian estimate V hat, conditional expectation of V of X, conditional on R, where R is the representation of that particular option. That v hat should depend on the elements of the vector boldface R, but it should be independent of the internal representations of the other options. It should have a probability distribution conditional on a complete description of what the situation really is that only depends on boldface X. It should be independent of what the other elements of the choice set are. So again, we should get the prediction of stochastic transitivity. We should get the prediction of regularity. We shouldn't be able to observe these kinds of systematic cycles or decoy effects that I was talking about. And the model that I talked about in the previous lecture, a simple model of lottery valuations, actually had these properties. So it was not yet a model that would imply that in choices between lotteries, we would see stochastic transitivity or violations of the axiom of regularity. So how could we get those things? Well, those results, though, depended on assuming that the characteristics of the different options in the choice set that are being considered simultaneously are in fact encoded or represented in the brain of the decision maker independently, with the noise in each of these independent representations assumed to be independent noise from the noise in the other representations. So we could get a theory of choices being based on optimal Bayesian estimates of the value of the options that nonetheless implied that subjective valuations would on average have an average value which is context dependent for either of two reasons why those assumptions in that simple case were not true. One reason we could get context dependent valuations might be that even if we suppose that the subjective representation of each choice option depends only on the features of that option, that vector boldface X for the particular option, it might be that the optimal decoding, the optimal estimation of the value based on the internal representation might be context dependent if there's correlation in the noise in these internal representations of the different options. So if you notice on the previous slide, when I described circumstances in which the noisy coding model with Bayesian inference would imply stochastic transitivity and would imply regularity, I had the assumption not only of independent representations, but independence of the noise in each of those internal representations. Maybe there's correlation in the noise with which the different options are being represented. That could lead to context dependence, as we'll see. The second possibility is maybe the subjective encoding of each option is itself context dependent. And you might say, well, why would that be? Why don't you separately represent what you're being told about each of the options? And the answer is it could be an efficient use of a finite capacity for representing things in the brain to in fact have these internal representations not be each a function just of the characteristics of one of the options, but might combine or compare characteristics of multiple options in a single element of the internal representation. We'll see more of what I mean by that later in the lecture. I want to talk first about this idea of context dependence of the valuations coming from context dependent decoding, even though the encoding, the probability distribution of internal representations conditional on the true characteristics of one option is just a function of the characteristics of that option. And so this line of theoretical development is going to get contrast effects from a model in which the individual elements of an array are each represented with noise. The fact that you have to infer what the elements of the original array that the subject was told about are based on the noisy internal representation is going to give rise to a signal extraction problem. If the brain then has to produce an estimate of what the values might really have been based on these noisy internal representations. If furthermore, the encoding noise for these different elements of the array is correlated across internal representations that relate to different choice items, if we have correlation between these different internal representations, the component of noise in them, then the optimal Bayesian estimate of the value of a given element of the array is not going to be a function solely of the internal representation of what that element was. Why not? Because looking at the internal representations of other elements of the array can give you an information about what the noise component might be of the internal representation of one particular element because of the correlation that I'm hypothesizing between the noise. So in the presence of correlation in the noise, the optimal Bayesian estimate will depend on the representation of other features of the choice situation that can make the valuation of independent choice options context dependent. So I'm going to give you an algebraic example of this to show you how it works. Suppose that there are several magnitudes x superscript I. These might be different dimensions of the value of a single thing. They might be components of the value of different options. Right now, it's just a vector of things in your environment that are going to be internally represented. And I'm going to suppose that each of these elements, magnitudes x sub I, x superscript I, is represented by a separate internal representation r superscript I, and r superscript I is x superscript I plus a noise term epsilon superscript I. And the vector of all those noise terms, boldface epsilon is the vector of all the epsilon superscript i's, is drawn from a multivariate Gaussian distribution, and the noise is independent of what the true vector of characteristics boldface x is. And it has a mean, which is a vector of zeros, that boldface 0, and it has a variance covariance matrix, which is this capital sigma. And then the problem is we want to ask, what should the brain do processing this information if the brain has to reach a judgment about what the true situation described by the vector boldface x is? It has to base this estimate only on the vector of internal representations, which is boldface r. One simple theory of what it would mean to construct an optimal estimate of what the true situation is to ask what the Bayesian posterior mean is for the elements of the vector x, the elements boldface x, if they have to be estimated based on this set of internal representations, the vector boldface r. So our hypothesis is that the vector of estimates, boldface x hat, is the conditional expectation of boldface x conditioning on the vector of internal representations, boldface r. So that's exactly the same kind of problem I talked about in the previous two lectures, except then I was talking about one-dimensional versions of the problem. There was a single quantity x being estimated based on a one-dimensional internal representation r of that quantity. Now it's a vector of features of the environment x, and there's a vector of internal representations that are being used to form this optimal Bayesian estimate. The calculations are simple if we assume that we have a prior, which is also multivariate normal. So we assume our prior is that the vector of characteristics boldface x is drawn from a multivariate normal distribution with a mean of vector of zeros and a variance covariance matrix, which is some matrix capital omega. Okay, so the signal extraction problem now is boldface x is drawn from this multivariate Gaussian distribution. Boldface r is boldface x plus a vector of noise terms, boldface epsilon. The noise terms boldface epsilon are a vector drawn from another multivariate Gaussian distribution, also with a mean that's a vector of zeros, variance covariance matrix boldface sigma. And so now we can ask what's the optimal estimate of x if the estimate has to be based on boldface r. If we assumed that the different x's were independently distributed under the prior, as I was in the last lecture, that would mean this capital omega would be a diagonal matrix with the diagonal elements indicating the prior uncertainty about each of the elements of x, but no off-diagonal elements. And if we assume that the encoding noise for the internal representation of each of those quantities, x superscript I, is also independent noise in each case, then the matrix capital sigma is a diagonal matrix. Each of the elements of the diagonal indicate the degree of noise in the internal representation of each of those quantities, but there are no off-diagonal elements. There's no correlation across the different types of noise. In that case, we can break the signal extraction problem into a separate problem for each of the elements of the vector x, and the optimal estimate of x superscript I, x hat superscript I, is just the conditional expectation of xi conditional on ri. it's going to be independent of the internal representation. So the other magnitudes, it's going to have a probability distribution which is independent of the true values of the other magnitudes. It'll only depend on what the true value of xi is. The problem I talked about in the last lecture was like that because it made things simple. Now I want to talk about what happens if the assumption that the variance covariance matrix capital sigma is not diagonal. We allow for the possibility of correlation. In general, we're not going to get that separation of the different signal extraction problems. In general, again, some of you will immediately recognize this as a linear regression problem. The optimal estimate of the vector x hat, boldface, is some matrix B prime multiplying the vector of internal representations R. That B prime, that's a matrix of regression coefficients, and it's what you probably recognize as the ordinary least squares formula there. We take the matrix omega plus the matrix sigma, invert all that matrix, multiply the inverse matrix into the matrix omega. That gives you B. Take the transpose of B. Okay, that gives us our vector of optimal estimates. And so it depends on the prior uncertainty and the nature of the noise in the internal representations. As an example, for those of you who don't immediately see what follows from those matrix inversion formulas, I'm going to work out a simple example of how correlation can lead to a context effect. Suppose that we have, in fact, a prior where under the prior, the different magnitudes x superscript I are all independent of each other. So x superscript I is drawn from a univariate normal distribution, and suppose they're all drawn from the same univariate normal distribution. So the uncertainty, the prior uncertainty omega squared is the same for all elements of the vector, but the noise component of the internal representation has both a common component and an idiosyncratic component. So the epsilon I for each of these quantities is the sum of a random term u plus a v superscript I. The u is a Gaussian random variable common to all components of the vector. The v superscript I is an idiosyncratic random, normally distributed random term, independent for each of the different i's. Okay, so that's a simple kind of model of the nature of the noise in the internal representation that allows some correlation. Now we can solve using my matrix inversion formula. I can tell you exactly what the matrix B is, and it's a certain multiple of the identity matrix, boldface I, minus a positive multiple of EE prime, where this boldface E is a vector, all of whose elements are ones. And the n in this formula is the number of elements in the vector boldface X that we're having to estimate. Okay, so that's telling us what the nature of the optimal estimate of x hat is. And you notice that the optimal estimate of any element of x hat does not just depend on the corresponding element of boldface R. If we had only the identity matrix in there, then it would be B would be a diagonal matrix. Each element of x hat would only depend on the corresponding element of boldface R, but it's not a diagonal matrix because there's this EE prime part, which is not a diagonal matrix. And so we're getting context effects, and we see what the sign of the context effects are in this particular case. So the optimal estimate, now we can ask what the optimal estimate of any given element of the vector. X hat superscript I is the optimal Bayesian estimate of what xi is for one element of the vector. We can ask what on average that estimate will be, conditioning on the true boldface X. So the true situation, which specifies not just what xi really is, but what all of the x's really are. And the answer in this multivariate normal case is that the optimal estimate will on average be a linear function of the x's, but it will depend not just on what xi is, but also on what the average of all the x's are. So this x bar is the mean of all the different xj's, averaging over all n dimensions. And what you see is that on average, the Bayesian estimate of xi will be this multiple of xi minus a positive multiple of the average value of all the features x bar. So we're seeing a contrast effect here. Xi's estimate x hat I will on average be bigger when xi really is bigger, but it grows with xi for a given value of x bar less than 1 for 1, because that multiplicative coefficient out on the front is a positive quantity between 0 and 1. And it also depends on what the average x bar is. So it depends on what the other x's are, even though under the prior, they are distributed independently of xi. And what you see is that the other x's being bigger for a given value of xi is going to make the average estimated value of xi smaller. So we're going to get a contrast effect where other things being bigger makes xi be perceived to be smaller for any given true value of xi. Okay, that's a feature of many well-known perceptual illusions. For example, many well-known visual illusions that we see contrast effects of this kind. Something to notice about it is that this theory predicts that the strength of this contrast effect should depend on there being substantial correlation of the observation noise. And it also depends not only on positive correlation of the observation noise, but it also depends on the true values, the correlation of the x's, the different xi's under the prior not being too large. In my mathematical example on the slide, there's 0 correlation under the prior of the true values. There's a positive correlation of the noise in the internal representations. And more generally, there could be correlation in the true values, but there has to be more positive correlation of the representation noise than there is positive correlation in the true values for the context effect to have this sign. Okay, so here's a familiar perceptual example. It's probably a perceptual illusion that you've encountered before. The question here is there are 2 figures on the left, one on the left, one on the right. There's a central gray region in each of these figures. Which of those central gray regions is darker? If most of you have visual systems that work like most people's, it probably looks to you like the central gray region on the right is darker than the central gray region on the left. But if I take away the boundaries, and now you just look at those central gray regions, you should see that in fact they're identical. They're exactly the same shade of gray. It's just that they're surrounded by different borders, a very dark border in the left, a very light border in the right. So this is an example of a contrast effect. It seems that the central gray region looks darker when it's surrounded by something which is on average very light, and it looks lighter when it's surrounded by something that is on average very dark. And that's like the formula at the top of the slide here. The x hat I is the estimate of the degree of darkness of that central region, conditional on the information that the brain is getting about the amount of light coming from all the different regions. A higher value of x bar is making xi seem to be smaller. So a higher average darkness of the whole figure makes the central region for a given value, true value of xi, appear to be smaller. Okay, so that's an example. A Bayesian explanation of brightness illusions of this kind is in fact very familiar in the vision literature. Edward Adelson has a paper from 2000 about exactly this class of illusions. The hypothesis about what the brain is actually organized to try to estimate, and what the Bayesian theory assumes that the optimal estimate is an optimal estimate of, is that it's assuming that what the brain is in fact optimized to do is to produce good estimates of whether objects in the visual environment are darker or lighter in a particular sense, not whether more light is coming to your eye from one object than from another object, but what is the reflectance of those objects in the sense of how much of the light that falls on them do they reflect. Okay, so some objects are darker in the sense that they don't reflect much light, other objects are lighter in the sense that they reflect more light. The available internal evidence to the brain isn't direct evidence about reflectance of objects in the environment. It's a report about the luminance of different parts of the visual field, how much light is coming to the eye from different directions. That luminance, which is what the brain gets more directly a signal about, is the product of the ambient illumination, how much light is falling on the object, and then how much of the light falling on the object gets reflected. So it's illumination times reflectance that determines the light coming to the eye. This is why the brain faces, according to Adelson, the brain faces a signal extraction problem because it wants to produce an estimate of the reflectance of different things that are in the visual environment. It has to infer reflectance from something that is affected both by reflectance and by the ambient illumination. We can map that exactly into my little mathematical model. If for each part of the visual field, x superscript I is the log of the reflectance of the object at that point in the visual environment. Epsilon I is the log of illumination at that point in the environment. R superscript I is the log of the luminance, the logarithm of the amount of light reaching the retina and passed on to the visual cortex from a particular point I in the visual environment. So our simple model said that Ri is equal to Xi plus epsilon, because luminance is reflectance times illumination. And if I have a multivariate Gaussian model now of both the prior about what the Xi's are and of the distribution of the vector of epsilons, I can use my model to make predictions about brightness illusions. I can get the prediction, the optimal estimate of local reflectance at a given point in the environment is going to be affected by the average reflectance of items in the object's context. A crucial part of this argument, though, was about the relative correlation of the Xi's under the prior and the epsilon i's under our model of the observation noise, and why that assumption could make sense in Adelson's model is that it makes sense to expect illumination to be relatively similar across nearby locations. So if you're in a brightly lit room, everything you're looking at is pretty well illuminated. If you're in a dark room, everything you're looking at is not very well illuminated. So one expects, typically we encounter environments where there's a lot of correlation between things we're looking at the same time in the degree of illumination, while the reflectance of different objects in the room can vary much more sharply. And so the hypothesis that there's much less local correlation of the true reflectance than there is of the local degree of illumination, in fact, makes sense as a prior to have about the statistics of visual environments. And so the Bayesian model with particular assumptions about the correlations could indeed make sense there. Okay, so that's an application in vision science of this idea of how contrast effects can in fact follow from optimal Bayesian inference under a model of the nature of the imperfect information available to the brain. Could it provide an explanation for contrast effects in economic valuations? Well, we would have to ask, why is there not just noise in internal representations, but why might that noise involve correlation in the internal representations of components of value of the different options that a decision maker is choosing between? And the answer is, well, suppose you're choosing between several different choice options. Suppose you're choosing between snack items, like in some of the experiments that involve food choice that I talked about back in the first lecture. In assigning values to these choice options, the decision maker, in fact, cannot directly observe the pleasure that they would get from the choice options. Now, in economic models, we typically assume, well, people know their utility function. You know, they just know from a description of what you get from the option, they can look up in their utility function how much utility they're going to get from choosing that thing. But if you ask in reality what people have to do when they're faced with some choices, they have to either draw on memories of past experience, so there are different snack foods in front of you. You have to think about past times when you've eaten those things and try to remember how you liked it or didn't like it, or you have to engage in mental simulation. You know, you are told or you can see characteristics of the thing you're choosing, and you perform a mental simulation of imagining eating that thing, and you see in that mental simulation how much you think you imagine yourself liking what you're going to do if you get the particular thing that you're choosing. In either of those cases, there's the possibility of either these memories of past experience or the outcome of these mental simulations being distorted by noise in the process, and memories of experience with similar items could be distorted in similar ways. So you're trying, or in the case of the simulation of outcomes of choices that involve similar features might involve noise in the mental simulation, which is again similar because the same simulations are being drawn on, or some of the same past memories are being drawn on, and try to remember or to try to simulate how much you like things that have given features. And those components of noise can be different at different points in time. Say they can be affected by the mood of the decision maker at a particular point in time, but they might be affected by aspects of the current internal state of the decision maker in ways that are similar for choice options that have similar features. So in fact, it makes sense that there can be correlation in the noise with which one evaluates the choice options, either by recalling past experiences or by trying to simulate what you would get mentally from consuming those things in ways in which it's quite natural to expect more positive correlation in the noise in the case of more items that are more similar in their features. And so that's the idea we want to propose. Paolo Nathanson, in fact, in his JPE paper, has a very nice discussion of this. He develops a theory of context effects in choice of exactly this kind. So Nathanson's model is one where choices between a set of items in a choice set are assumed to be based on what he calls noisy signals of the value of each of these options. These are the noisy mental representations I've been talking about, which could be a noisy recollection of past experiences or a noisy outcome of a process of mental simulation. Anyway, he assumes there's a random signal of the value of each of the options in the current choice set. Context effects in Nathanson's paper result from the fact that the noise in these signals corresponding to different items in the choice set are allowed to be correlated. In his theory, he assumes that the decision maker has evolved the decision rule, which can make use of this known correlation in the way that it forms Bayesian estimates based on the noisy internal representation. So the correlation is optimally taken into account. Nathanson's model is a little more complicated than my simple model above, where I worked out the calculations explicitly under the assumption that the measurement noise had a common component and an idiosyncratic component, and that was the entire nature of the correlation. It was just the relative variances of the two components that determined the correlation. Nathanson allows for more complicated correlation patterns. What he assumes is that there's more correlation in the value representations of goods that are more similar to each other. And he has some somewhat intuitive discussion of what would make different choice items more similar. But basically, in his theory, similarity is only defined in terms of the degree of correlation in the signals of different goods. However, the mathematical structure of what similarity can be like does imply that there are testable restrictions of the theory. So this theory is going to allow a more complex pattern of bias than in that simple example of contrast effects that I worked out above. In the example above, the average Bayesian valuation could depend not just on the true xi, but on x bar, the equally weighted average of the values of the other things. That would result in a bias in estimated values, but you would expect the bias to be the same for all goods. They would either, on a given occasion, all be overestimated because x bar is low on that occasion, or all be underestimated because x bar is high on that occasion. And that wouldn't result in bias in choice. To get biases in choice, we want there to be biases in subjective valuations, which bias the valuation of some elements of the choice set more than they bias valuations of other elements of the choice set. So we need this more complex pattern of correlation that Nathanson is going to allow. Okay, so how does his model? He calls it a Bayesian probit model. The way it works is the value of each choice option I is going to be based on a noisy internal representation. He assumes that for each choice option I, there's a single univariate signal R sub I, which is just the true value to the decision maker of option I, that V of X is some function of the vector of characteristics for option I. So option I is now the option, boldface X with a subscript I is the complete vector of characteristics of choice option I. V of that vector is the correct valuation to this decision maker of something with that vector of characteristics, there's going to be a univariate internal representation, R subscript I, which is that single number, V of boldface Xi, plus a single random term epsilon sub I. So like in an additive random utility model, we're assuming that that R sub I, this internal representation, is drawn from a random distribution, and it depends only on the goods characteristics, boldface X subscript I. It's going to depend only on the characteristics of good I through the utility index, through this aggregation of the different components of X sub I, through this function V of X sub I, which depends only on the characteristics of good I, is independent of the characteristics of the other goods of the choice set. So far, it's exactly like an additive random utility model. The difference from a standard additive random utility model is that in the additive random utility model, we called this thing not R sub I, we called it V tilde. We called it the subjective assessment of the utility, or the value of item I, and we said the subject chooses the item for which V tilde is the biggest. That's not what Naughtonson is going to assume. Naughton is going to assume there's the random signal R sub I for each of the items in the choice set. The subject is going to form an optimal estimate of the value of V of X for each of the items, conditioning on the noisy internal representations, and they're going to choose the item for which the estimated value is highest, and the estimated value is not the same as the R sub I itself. How is it going to be different? It's going to be that conditional expectation of R sub I, conditional on the whole vector of internal representations. The noise terms epsilon I for the different goods in the choice set are going to be assumed to be drawn from a multivariate Gaussian distribution, represented in this way. There's this parameter T in it, which is a scalar index of precision that you could assume varies with time if you wanted to ask how time pressure would affect the nature of random choice in this model. I'm not going to talk about that here. So that's just some positive factor. The main thing we're interested in is this sigma, and whether the matrix sigma has off-diagonal elements that imply that the different noise terms are correlated. So Naughtonson assumes that the diagonal elements of the matrix sigma are all equal to 1. He uses that T index of precision then to determine how big the diagonal elements of the variance covariance matrix of the epsilons are. And that's assumed to be the same for all of the goods in the choice set. The off-diagonal elements of sigma are then the other parameters of interest. Sigma subscript ij, the off-diagonal element corresponding to goods I and j, is going to measure the correlation between the noise terms epsilon I and epsilon j. So the noise terms in the internal representation of the value to the decision maker of goods I and j. Okay. He assumes that for any two goods, you can have a correlation between the noise terms. He assumes that the correlation is bigger depending on the degree of similarity of the goods. If I and j are goods that are more similar, he assumes a larger positive correlation, sigma sub I sub j. The greater the positive correlation, he supposes the goods are more similar. The idea here is that similar goods should be easier to compare. So there'll be less randomness in the choice between the two goods for a given degree of closeness of their true valuations. And we can see that if we just consider a binary choice. The choice is just I and j. We have the two noisy internal representations, Ri and Rj. Under the theory, the probability of choosing j over I, when the choice set is just those two items, is the probability that v sub j plus epsilon j is bigger than v sub I plus epsilon I, where the vi and the vj are the deterministic component of the valuations, or the correct valuations to the decision maker of the two goods. The epsilon j and the epsilon I are the correlated noise terms. And in our multivariate Gaussian model, the probability that vj plus epsilon j is bigger than vi plus epsilon I is this formula at the bottom of the slide, where capital phi is the cumulative distribution function of the standard normal distribution. Again, it depends on the difference between vj and vi. Vj minus vi is in the numerator of that expression, but it also depends on the amount of correlation of the noise. You see the sigma ij is in the denominator, And so what that says is that for a given value difference, a given amount by which Vj is in fact bigger than Vi, holding that fixed, if we increase the correlation of the two noise terms, we make sigma ij bigger and closer to 1, the denominator gets smaller, the argument gets bigger. That means that the choice probability gets further away from 1/2. Closer to 1 if Vj is bigger than Vi, closer to 0 if Vj is less than Vi. So it's saying that if the goods are more similar, implying more correlation than in their internal in the noise in their internal representations, choice will be more predictable because he says the goods are easier to compare. Okay, so that's how you might think it makes sense for more similar goods to have more correlated internal representations. Now, suppose that we consider a model where the prior is again one where the true values, the V sub i's, are independently distributed under the prior. So under the prior, the value of any one of the goods is uncorrelated with the true values of the other items in the choice set across different choice problems. In that case, we can now work out what the optimal Bayesian estimates are. It's that same formula I used before, but now using Nautanson's assumption about the noise structure. And by inverting a particular matrix, we can define V hat as a multiple of the vector of R's. If that matrix is not diagonal, the estimates in the V hats will depend, the V hat for any given good I will not just depend on Ri, it'll also depend on R sub j for goods j different from I. In general, that means adding a new option to the set whose values are being estimated can change the estimated value of a previously existing option. If we had two previous options, A and B, we could compute this vector of subjective estimates. It'll depend on the vector of internal representations. If we add a new good, we're now going to have a new element in the vector of internal representations. If the noise with which that new good is represented is it correlated with the noises of the other internal representations, having a new element in the vector can change the elements of this matrix in a way that changes the degree of sensitivity of V hat to the true characteristics of those original options. If we suppose that we introduce a third good, which is a decoy good, in the sense that it's dominated by one of the existing options, but it's asymmetrically dominated. It's dominated by option A, but not dominated by option B, say, of the original goods. If the decoy D is dominated by some existing option I, Naughtonson assumes that comparison between those two goods should be easy because the comparison goes the same way on each of the features of the goods. One good is better than, or at least as good as, the decoy on every dimension, so it should be an easy comparison. He models that as saying that sigma ID, the correlation between the noise terms, should be particularly high in the case of two goods like that. If we assume sigma ID is more correlated than the correlation between the noise for the decoy good D and other goods J that don't dominate the decoy, then the inclusion of the decoy in the choice set is going to have a particularly strong positive effect on the estimated value of option I, a bigger effect than it has on the estimated value of the other goods. That can then change relative valuations in the way that the decoy effects observed in the marketing literature do. Okay, this is an illustration that his model can work quantitatively in the data I just showed you for the experiment with the frogs. We've already talked about the data. Now we also have the predictions of Nautanson's Bayesian probit model if he parameterizes the true values of the options to the decision maker and the assumptions about the correlation of the noises in a particular way. So here, the left part of the panel and the lower part of the slide is the data that I showed you before. The right part of the same table labeled BP, those are the theoretical predictions of the Bayesian probit model with the parameters at the top of the slide. What do the parameters at the top of the slide say? The mu B, A, and C over at the left are the true values of those options, the things I was calling V of X on my previous slide. And so he's assuming that the true value of mating cry B to this decision maker is slightly bigger than the value of A. B is somewhat more valuable than A, but C is a lot worse than both of them. Mu C is -1, whereas both mu B and mu A are not too different from 0. Okay. Secondly, to reconcile what's going on with the experimental data, he assumes some positive correlation in the noise in the internal representations of all three of those values, but he's assuming that sigma AC is quite high, 0.8, whereas the correlation sigma BC is quite low. So what does that mean? That means that A and C are relatively easily comparable, whereas B and C are not so easily comparable, according to this assumption about the noise. And that made sense if one recognized that A and C was a case where you had almost a strict dominance relationship, whereas B and C, definitely C was much better than B on one dimension. C was the decoy. C was much better than B on one dimension, but B was much better than C on the other dimension. So one might think that that's a particularly hard comparison to make, and that's represented by little correlation in the noise. If you plug in those parameters, the predictions are qualitatively quite similar to what was observed in the experiment. So when the choice set is just A and B, B is chosen more often than A, but not a whole lot more often. When you add C to the choice set, now A is chosen more. And if you have C be audible, but not choosable because it's coming from a speaker up on the ceiling, now the amount by which the choice of A increases is even greater. A is chosen more than 60% of the time in that case, whereas A was only chosen a little more than 40% of the time when the only choices were A and B, and C was not audible. So it's producing the decoy effect. And similarly, it could explain it in human marketing experiments using parameters of a similar kind. Okay, so does that answer all of our puzzles? The answer is no. If we ask whether we can get preference cycles in binary choices of the kind that we saw in the May experiment, the answer is no. I've already shown you what the model implies about a binary choice between just some option J over I. Probably when the choice set has only I and J in it, probability of choosing J over I is given by this formula. And you notice that that implies that J will be chosen over I more than half the time when it's just a binary choice set, if and only if Vj is bigger than Vi. And so that means that we should still have stochastic transitivity implied by this model if we look at different binary choices. So May's kind of results where we were seeing a violation of stochastic transitivity because there were frequent cycles of a particular kind among three choices, according to what was chosen more often, is not going to be consistent with Natanzon's theory, although it does get some kinds of context effects. That gives me a reason to talk about my other possible reason for context-dependent valuations in a Bayesian model. Context dependence coming from the nature of the encoding, the nature of the way the values of different contributions to value of different things are being encoded in the internal representations. And the other possible theory that I mentioned back at the beginning of the talk, which is also a line of development that's also found in the perceptual literature, is to suppose that instead of the absolute magnitudes of various features of the environment, each being independently encoded, that relative magnitudes are either often encoded or encoded entirely rather than absolute magnitudes being encoded. So in other words, comparisons between different features of the environment are directly what are internally represented. It's differences or relative values that are represented rather than the absolute values that are represented. If one assumes that in the internal representation, the thing that's represented in noise is directly various comparisons, then when you try to decode, optimally estimate absolute values from the internal representations, those absolute values that you estimate, even though it's an optimal estimate, will on average turn out to be context dependent. This idea that what are encoded in internal representations is in fact something that can be demonstrated by sensory data, by actually looking at what how different cells respond to variations, different cells in sensory cortex fire in response to variations in the sensory environment. And it's clear that many of these regions of the brain involved in sensory processing are providing a lot of information about contrasts in the environment rather than just providing information about, say, the degree of brightness. So contrast between lightness and darkness of nearby regions in the visual environment is encoded a lot. The absolute level of brightness at an individual single place in the visual environment is not what nearly as many cells seem to be encoding. And this idea that internal representations might be mainly reporting on contrasts between different features of the economic options that are present is something that has also been proposed by various authors trying to explain choice biases. So this famous paper by Tversky and Simonson from back in the 1990s was one example. They hypothesized that people choose the way they do because choices are based on comparisons rather than being based on the absolute values of the features of each of the individual choice items being used to estimate the value of those items. The salience theory of Bordalo, Genioli, and Schleifer in the economics literature is a theory that has that same flavor. More recently, in these theories, however, this is simply being postulated as something that seems to explain context effects in choice. Here, I want to discuss the idea that it might be a characteristic of optimal estimation of the value of things under a particular hypothesis about what the nature of the imperfect information is in imperfect internal representations. So suppose we hypothesize that two options are going to have to be compared in a binary choice problem. The two options each differ along multiple attributes. And suppose that instead of as in Nautenson's model, that a given option that's defined by a vector of features, boldface X, instead of combining the elements of boldface X in a single number, the scalar value V of X, that's then going to be imprecisely encoded, suppose that the values of these different attributes of the choice items are separately being encoded. And that's like in our model of lottery choice, where rather than evaluating the expected value of the lottery and then encoding that with noise, we were supposing that information like the payoff and the probability could be separately encoded with noise, and then or payoffs in different states of the world could be separately encoded with noise, and then these separate pieces of information had to be combined later to estimate the value of the choice option. So we're going to suppose that here. We're going to suppose the true value of the choice option is just the simple sum of the different components of X. So the different elements of X are different features. More of each of the features are good. The true value to the decision maker of an option is the sum of the features X sub A, where A indexes different attributes of the choice option. But instead of encoding the sum of the X sub A's, each of the individual X sub A's is going to be separately encoded. But suppose now, furthermore, that for each of these individual attributes A, we can look at the value of each of the two choice options along attribute A, and suppose that rather than X superscript I is the option, is the choice item, A is the particular attribute, the subscript, instead of that XIA, the value of the particular attribute for the option I being separately encoded for each of the two options in the choice set, suppose it's the value difference, the difference between X2A and X1I. So with respect to feature A, how much better is choice item 2 than choice item 1 with respect to that feature? Suppose that value difference with respect to attribute A is the thing that is imprecisely encoded by an internal representation R sub A. The subscript is now that the element of the vector of internal representations, there's going to be one for each of the attributes A. And suppose the choice now between item 1 and item 2 has to be based on this vector of noisy internal representations, R sub A, for the several attributes. Okay. So I'm going to walk through a simple example, consider a simple example in which the distribution of each of the elements in the vector of noisy internal representations conditional on the true value difference along that dimension is in fact independent. So there's not going to be correlation across the noise in the different elements of the vector of internal representations in this example. So the kind of correlation Nathanson's results depend on is going to be assumed away to simplify things, but instead of assuming a prior, as in that Nathanson calculation, where the true values of the different items in the choice sets are uncorrelated, I'm going to assume a prior, or rather, I am going to assume a prior in which the different attributes are distributed independently of one another, but we're going to assume that it's the value difference with respect to each attribute that's being encoded with noise. Okay, under this assumption, the optimal Bayesian decision rule is going to be a decision rule that maximizes the expected value of the item obtained, and it'll be the decision rule that says I should choose option 2 over option 1 if and only if, conditional on the vector of noisy internal representations, the mean of v of x2 minus v of x1, estimating that thing conditional on my vector of internal representations, is positive. That conditional expectation under these independence assumptions at the top of the slide, that conditional expectation can be broken into a sum of terms, independent terms for each of the different attributes A. So summing over the attributes A, we compute a conditional expectation of delta x sub A, conditional on RA. We do that independently for each attribute, sum those conditional expectations up, and ask whether overall that sum is positive or negative. That determines whether on that trial the decision maker should take option 2 or option 1 of it. So we're using the independence both in the prior and of the encoding noise to simplify the calculation. Now we get univariate problems of the kind I've talked about a lot in these lectures. If R sub A provides precise enough information about the true value difference, this assumption that only the value differences are encoded is not going to lead to any error in choice. So that assumption is not necessarily one that is bad for the decision maker at all, because if R sub A provides sufficiently precise information about delta XA, then you're going to be able to have very accurate choice and therefore be very close to perfect utility maximization. But if we assume now that there's a limit on the precision of the internal representations, then R sub A may not provide at all precise information about the exact value of delta XA, then this decision rule can imply valuation errors, and it can easily lead to preference cycles. And if you want to see how it can lead to preference cycles, I'm going to talk about a very simple example where the degree of imprecision in the internal representation is pretty extreme. Suppose R sub A can only record a binary value. It has to either say up or down, yes or no. It can only take the 2 possible values. And so then the best possible signal subject to that constraint is to record the sign of delta XA, say whether the sign is positive or negative, but you're going to record R sub A will be +1 if delta XA is positive, R sub A will be -1 if delta XA is negative, and it can't record any more information because that was our constraint on the available complexity of the internal representations. Then if each of the true values of the 2 attributes is an independent draw from the same prior distribution, we can calculate what the conditional expectation of delta XA, conditional on the internal representation R sub A is, and it'll be some constant multiple of R sub A. It'll be a positive plus K when R sub A is positive. It'll be minus K when R sub A is negative. What the K is going to depend on the prior distribution of the differences in X sub A. I'm assuming that's the same for each of the attributes. So the K is the same for each of the attributes. So then the model predicts that option 2 will be chosen over optimal 1 under the optimal decision rule, if and only if the sum of the R sub A's is positive, because the sum of those conditional expectations will just be a positive factor K times the sum of the R sub A's. The R sub A's are all +1s and -1s. So the sum will be positive if and only if there are more +1s than -1s, which means the choice will be in accordance with that majority rule heuristic that I mentioned earlier. If 2 is better than 1 on a majority of the attributes, you'll go for 2. If 1 is better than 2 on a majority of the attributes, you'll go for 1 instead of 2. But I've already shown you that choice in accordance with the majority rule heuristic can give rise to preference cycles in examples like Mez. Okay, so we can explain preference cycles. We can also explain decoy effects. I won't go ahead and talk about that. Since I'm out of time, let me jump to the conclusions. I think it's possible to explain seemingly irrational choice biases as reflecting optimal patterns of behavior, optimal in the sense that they do, in fact, maximize the expected value to the decision maker of the things that they get from their choices if we average across all of the possible choice situations, and we assume that the choice rule is subject to the constraint that the decisions have to be based on these imprecise internal representations. Furthermore, the internal representations we have to assume are not themselves contrived in a crazy way, although I didn't have time to talk about this as much as I wanted to. The nature of the imprecision that we have to hypothesize to get these contrast effects can itself be expected value maximizing, subject to a constraint on what the feasible complexity of internal representations are. And I hinted at that in my discussion just at the end of the lecture. Such an interpretation, I think, offers us the prospect of a more unified explanation of behavior than a lot of the work in behavioral economics might seem to offer, where people collect evidence of different kinds of anomalies, but it might seem that there's simply a collection of different claims about generalizations about behavior that don't add up to a unified theory. Furthermore, I think an advantage of this kind of interpretation is that it is going to allow us the possibility of welfare analysis on the basis of what we infer about people's own internally consistent true preferences. But we're going to do that without identifying every observed choice as reflecting their true revealed preferences. So we're going to interpret some of the choices people make as random and even as being based on subjective valuations that involve systematic biases, but underlying the theory, there will be a true objective that the decision rule is in fact optimized to maximize. And so we'll be able to make inferences about people's true objectives and base our welfare analysis on that. Traditional behavioral economics, I think, doesn't make it obvious how you should do welfare analysis. And so this is one of the reasons why I'm interested in this program. A further lesson I hope you've gotten from these lectures is that trying to understand the mechanisms that underlie similar biases in perceptual contexts can shed light on the nature of the relevant constraints on the structure of and the precision of internal representations. And so I think this can help us in theory development in this direction. I hope I get some of you interested in pursuing this further. It's a relatively new topic of investigation, but one that I think is rich for implications for the development of economics.
Okay. Thanks, Michael, once again for excellent illustration of the problem and the bias that you have said due to the preferences and the valuation issues were discussed. Now, of course, we had actually extended a couple of minutes scheduled time, and the organizer had announced that they are going to have a breakout sessions. So in that case, I think we do not have much scope to discuss here. And if those who have registered for the breakout sessions, please you look at your mail. The organizer might have sent you the different link. You need to go and join there. I can't see any specific questions in this session, so that means you can carry out some of those questions for fresh interaction there in the breakout sessions. But of course, there are some issues.
I suspect there are some questions, and I'll be happy to join you in the breakout sessions in a few minutes.
Yes, so I had definitely something, but of course, for the benefit of the time, I don't want to raise it here. And so with that, I think I'd like to thank you on behalf of the Delhi School and the University of Delhi. I'm really grateful that you found time and you managed to get time to deliver the illumination lectures. And of course, I see our students, the scholars, those who have attended, have got enough food for thoughts to pursue their research careers and take out some of those issues for their own careers. With that, once again, I'll thank you, and I'd like to also conclude this session here. Please join the breakout sessions in 15 minutes time. Look at your email IDs, you might have get the link. Thanks, Michael, once again.
Okay.
Thank you very much, Michael.
So hope
Yes.
that we'll find some time. Once, I guess, we'll come back to the normal situations, and I mean, we'll find an opportunity to invite you once again in futures, hoping. With that hope,
That would be very nice. Thank you all for listening.
Thank you very much. Thank you so much.
So, Somendu, shall we leave now then?